¿Me oyes, Enrique? ¿Tú sabes lo que hacía todos los días para comprobar el buen tiempo? Todos los días era de buenos días, son las 8. Está el tiempo parcialmente nublado. Buenos días, Enrique. ¿Cómo está el día por el Indes? ¿Por Jerez? ¿Está lloviendo, Enrique? Bucle.
Como lo voy a silenciar ya.
Me asusto. Sí. Pero con el móvil, dices tú. Pero lo tengo, con el móvil sí lo tengo todo silenciado. De hecho no estoy en Google Meet. En YouTube lo cierro todo. No estoy en nada ya. ¿Enrique sigue sin oírme? ¿Hablo? ¿Me estás escuchando? Uy. A ver, si hay un retardo es normal. Lo raro sería que estuviésemos hablando a la vez. Buenos días, buenos días. Enrique. Buenas, Enrique. Enrique, a ver si va a ser que tienes apagado los altavoces. Pero sí lo hemos visto ni entrar. Buenos días, Enrique.
Me deja otro.
Pero que el problema... Te quito el canon y ya está. Ah, ¿tú dices la corriente le quito? No, que lo que le iba a quitar era el canon, para no apagarlo. ¿Hablo, Enrique? ¿Me escucha, Enrique? Sí. ¿Qué? Sí. No podemos estar. No se puede interactuar por videollamada entonces. Claro, que aquí no se escucharía de ninguna forma porque estamos acá.
Ya estoy, Amalia. ¿Me escucháis bien? ¿Amalia? ¿Hola? ¿Me escucháis? Hola, 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 hola. ¿Qué tal? ¿A mí me escucha? ¿Me escucha? ¿Me escucháis? Hola, hola, hola. ¿Qué tal? ¿Todo bien? ¿Todo correcto? Vale. A ver. Fijar. ¿Ya la ha cambiado Noemí? Hola. ¿Me escucha Noemí? Noemí, ¿me escucha? Noemí, ¿me escucha Noemí? Noemí, ¿me escucha? ¿Qué tiene puesto? Que no lo veo. Ay. ¿Me escucha Noemí? ¿O no me escucha? Vale, te lo grande ahora. Hola, ¿me escucha? ¿Me escucha Noemí? ¿Me escucháis o no? Te estoy viendo en el Meet. Si quieres, levanta la mano si me escucha. ¿Me escucháis? Hola, hola. Hola, Noemí. ¿Qué tal? ¿Me escucha? Hola, hola. Hola. Hola, hola. Hola, hola, hola. Hola, hola. ¿Me escucha Noemí? Hola, Noemí.
Tu Sevilla, sorry.
Que no está enterado.
Vamos a ver. Espérate que aquí, venga. Tiene que estar. No me lo han enviado. ¿A qué email me lo has mandado? Sí, pero vale. Presentation. Esta vez ya debería estar, vamos. No sé si hace un refresh y ya debería estar. La de ellos.
¿La de Simon Ribeiro?
Sí, esa es. Perfecto. Y te voy a pasar también, aunque está conectado. Yo la subo y después la cargamos. Vale, ya está adelante. Ya sabemos a ver cómo es el mismo, ¿eh? Porque esto sí, ayuda. Nunca funcionó.
El mic es después del cogido.
Las solas dos últimas.
Espérate que tengo que cambiar cosas aquí. Deja de presentar.
Una presentadora ahí.
¿Ya funciona? Habla por ahí.
Buenos días. No. Un poquito sí. Sí. Se oye.
Vale, si yo veo en YouTube algo. Se escucha. Pero Google Meet no. ¿Te puedes conectar a Google Meet desde tu móvil, por favor, y hablar? Decir hola, buenos días. Es que se escucha todo menos Google Meet.
Ajá, vale.
Me parece, porque YouTube probé antes y se escuchaba y ahora no se escucha. Este no debería de ser.
Este sí funciona.
¿No has cambiado la tarjeta de audio o algo?
Que no toco nada.
Ahora ha sonado, ya está.
Sí,
Hola.
Muévelo donde estaba ahí y
Perfecto.
nosotros lo miramos la cámara.
vale, pues así se va a quedar, pero
¿El equipo apagado?
porque yo voy a hacer así
Sí.
y lo voy a dejar más bajo. Ahí se escucha bien, ¿no?
¿Se lo encendí?
¿Debería silenciar este micro?
No, porque es por donde está entrando la llamada. Pero no está el micro del ordenador, está el... No debería.
No.
¿Hola?
Por eso, vamos. Espérate. ¿Por ahí no suena?
Buenos días. Buenos días. ¿Me estás escuchando? Sí, está entrando, sí.
Hola, hola.
No su- no, ahora sí, ahora sí. Pero lo estamos escuchando aquí abajo. Y silenciando ahí ese micro.
Hola, hola. ¿El volumen? Hola, hola. Hola, hola. Lo que pasa es que tiene mucho delay. Hola, hola. Hola, hola, probando, probando. Hola, hola, hola. Pues están probando para que funcione el... Pregúntale.
Audio Jungle. Audio Jungle. Audio Jungle.
Hola.
Probando, probando. Hola, hola. ¿Otra vez? ¿Ah, ya?
Yes, echo. Yeah.
Sí.
Sim.
So good morning to everyone. Sorry for the delay, sound problems. So it is my pleasure to announce the first speaker of the day. It's Pedro Ribeiro in a joint work with Semyon Yakubovic. The title, as you can see, is Poisson's summation formula and index transforms.
Thank you very much for the kind introduction. This talk will be a bit mixed, because I will talk about the main results. The main slides will be myself talking, but then Semyon will make some expert comments on the kind of stuff that I will talk about. So the plan for this talk is to first introduce the Riemann-Zeta function, and then to present a formula due to Bernd, Dixit, and co-authors concerning Bessel functions. A proof that in a separate work related with this, I found using the Kontorovich-Lebedev transform, and then the questions that arise from this new proof and the variants of this proof concerning the summation formulas attached to the index of a class of special functions. And then I will address some further questions. Okay, first I usually begin my these kind of presentations presenting the first protagonist of this kind of stuff, which is usually the Riemann-Zeta function. As most of you, perhaps all of you know, it is usually introduced in a course, Calculus 1 course, first course in analysis, real analysis, this series, which of course converges absolutely when, if I take the parameter s as real, when the parameter s is greater than 1 by the integral test, and diverges, of course, if the parameter is less or equal than 1. The interesting case s equals 1 due to Nicolò-Oresme, the divergence of the harmonic series. Of course, this was a great problem in the 17th century, how to evaluate the Riemann-Zeta function at the 2 or 4 or 6, etc. And there was this conjecture by Bernoulli that it was around 1.6 or something. It was they expected some kind of convergence and some values, and Euler discovered that, in fact, when we put the exponent equals to 2, then we have this relation. We have a relation between an infinite series of this kind and geometry, pi. This was the discovery that made Euler famous, the solution of the Basel problem. And then Euler, in a later paper, actually in the same paper, generalized this kind of thing. Like he discovered that the zeta attached to all even integers will be a power of pi to the whose power is the same as the argument of zeta. And this guy here, this B2k, is the Bernoulli number. It's a well-known rational number, usually coming from combinatorial problems. Euler, of course, knew about these kind of numbers because they appeared in a previous book by his mentor, Jacob Bernoulli, but actually these kind of things were known to Japanese mathematicians previously. But since Japan, since the Tokugawa, since the shogunate Tokugawa was isolated from the rest of the world, nobody knew about these contributions of Takakazu Seki. Okay, so let me, before going to the technical part of the talk, mentioning a long time interest of Professor Petronillo concerning the zeta function. I was a student in the year 2020 and 2021 at functional analysis course and special functions course, orthogonal polynomials and special functions course, constructive approximation, something. What was the name of the course? But the part that Petronillo taught us was, and Kenya, was the orthogonal polynomials. And he was not obsessed, but he really enjoyed the problem of the zeta function attached to odd integers. As you can see, I mean, when the argument is even, we have a power of pi. And you know, since Lindemann, 1882, that these kind of things are transcendental, because pi is transcendental. And the Bernoulli numbers are rational. So, okay. But the problem is, when the argument of the zeta is odd, what can we say about that? About arithmetic nature? And Petronillo really liked this problem. And he thought that the theory of orthogonal polynomials would be essential to solve this kind of this great problem. Of course, Apéry in 1979 proved that zeta of 3 is irrational. And then all kinds of things are known, like there are infinitely many values, odd values, for which zeta is irrational. We don't know which, but there are infinitely many. And we know by the Zudeelian that at least zeta 5, zeta 7, zeta 9, or zeta 11 is irrational, at least one of them, at least one. Which one? Nobody knows. From zeta 5 to zeta 69, it is also known that there are at least 2 values from that are irrational. But which one? Nobody knows. And in fact, there is a proof that zeta 3 is irrational using Legendre polynomials. And perhaps due to these polynomials, perhaps would be essential to solve. In the limit, okay, this has a limit, which is gamma. Nobody knows anything about this constant, but Conway said that he would like to live long enough to see a proof that this guy was irrational. And Petronelli once said me that he would like to live long enough to see a solution of that zeta 2n minus 1 was irrational. So this kind of thing, this is a tribute to him. So I would like to mention this, his interest in these things. So let me now explain briefly that after Euler introduced the zeta function, then Riemann complexified the Riemann zeta function. Now the called Riemann zeta function, before was Euler zeta function. And what Riemann did was like, he turned the product of gamma of s times zeta of s, when it makes sense, of course, as an integral of this type. Of course, this integral only makes sense when s is a complex number whose real part is greater than 1. Because if it's less than 1, this guy will explode at the origin, right? You have x to the s minus 1 at the origin. If the exponent is small, it will explode. But in fact, this integral can be deformed in a way that it remains valid for all complex values of s. And that's what Riemann did. He took this integral, it took a deformation of the path. Instead of the real line 0 to infinity, or the half real line, he took another path. Now the integral would make sense, and he proved a lot of things. He proved that the Riemann zeta function is analytic everywhere except with a singularity at s equals 1, where it has a simple pole. It has simple zeros, so-called trivial zeros at the negative even integers, and it satisfies a functional equation of this type. This actually says that, say me anything about zeta function on a part of the complex plane, then this tells how it behaves in the other part. And as you can see, the subset of the complex plane that remains invariant under this equation is precisely, what is it? Is a vertical line equals to 1/2, because 1 minus s becomes real part equals 1/2. It stays on the real line, on the vertical line. And if you take s equals 1/2 plus it, the vertical line with real part equals 1/2, it stays invariant under this transformation. And that's why the line of symmetry, which is given by the real part of s equals 1/2, is called the critical line. It's where all the symmetry of the Riemann zeta function relies on. And in fact, from this functional equation that Riemann discovered, one can easily check that this function here, pi to the minus s over 2, gamma s over 2, zeta s, is real, not complex value. S assumes real values when we are on this line. And this will be quite important somehow in a later slide, okay? So this function is real on this line because of this guy here, due to this invariance. As you can see, 1 minus s when we are on a critical line is the same as the conjugate of s. So this says precisely that the function here, eta s, is real. Not complex, real. That's important to introduce transforms here. Now I will talk about a bit of special functions, namely the other protagonists, the modified Bessel functions. If you take the usual Bessel differential equation and you slightly change the argument, if you turn x into ix by multiply by I, you get this modified Bessel differential equation. And if you formally solve it using power series, you get one of the solutions, which is this, the modified Bessel function of the first kind. And you can also impose another solution by taking this combination, and you get the Macdonald function, the modified Bessel functions of the second kind. And these are the protagonists of this talk, the special functions that will be mostly important in this talk, which are motivated by this problem from physics. Okay, there are other things like the first solution to Bessel's differential equation blows up at infinity, but the other one, due to the restriction, it goes down. It decays exponentially fast at infinity. Okay, both solutions have this behavior, this drastically different behavior. But as you all know, when we restrict the argument of the Bessel function, the index nu, perhaps to 1/2, we can recover elementary functions. So in some limiting cases, we always have a relation between elementary functions. In this case, hyperbolic sine of x, when the index is 1/2, and in the case of the Macdonald function, this e to the minus x. Okay, now a bit scary, this formula, but in 2018, Bernd, Dixit, Kim, and Zaharescu, motivated by the work of Ramanujan and Korslyakov, proved a general summation formula involving the product of Bessel functions. This was kind of motivated by a way to generalize some claims of Ramanujan, but the thing that they got was this. We have on one side a series involving a product of the modified Bessel functions, I and k. Note that these converge because of the condition x greater than y. Let me see why. Okay, k nu goes exponentially fast to 0. But this guy goes exponentially fast to infinity. But since the exponent of k nu is greater than the exponent of the argument of I nu, it is okay. The convergence is assured. But the difficult part is this one. Like, you have these arguments, and then the second series will involve the hypergeometric function. And they were interested in fixing some parameters, nu and nu in both cases, and get new formulas and recover old formulas from this kind of thing. And one that you get, not by fixing nu, but by letting y tends to 0, is this one, is a formula due to Watson. So when you take y to 0, the modified Bessel function of the first kind will become elementary, will become like this guy, something that does not depend on y. And then you plug in this formula, you plug in y equals 0 in this formula, the hypergeometric function will become a rational function by reduction formulas, and you'll get this, which is a very important formula due to Watson. Very important in the analytic number theory, this formula. It appears in the theory of Epstein zeta functions. It appears in Ramanujan's lost notebook somehow. And this is a particular case that they emphasize that it is a particular case of that formula. But their proof is very complicated. That means, just remind something. They use an analog of Voronoi summation from due to Guinan, whose conditions are very difficult. Actually, Guinan does not prove the formula, it's only formal. And they also do not prove, they indicate a proof, I think, but the proof by Guinan is a bit sketchy, not completely complete or rigorous, I would say, but it's correct, of course, because they don't need the full strength of Guinan's statement. They need a weaker one, which is, of course, correct, is due to Korslyakov. So all the steps are valid. They use evaluation of Hankel transform due to Korslyakov, which is also kind of difficult. And they use several transformation formulas for the hypergeometric function, which are not very easy to use. They use simultaneously several transformation formulas. But in fact, the corollary previously stated, this one here, Watson's formula, can be obtained by their formula, but as an independent proof, namely from the reflection formula for the theta function. And was because of this that when I started working on studying the number of zeros of some combinations of the Dirichlet series, I found this integral transform, which is in a table compiled by the supervisor of Semyon, Marichev, and Prudnikov, and Savishenko, which represents the product of two Bessel functions, which appears in the form of Bernd, Dixit, and the co-authors, in this way. So I immediately thought that if I wanted to reprove the formula of Bernd and co-authors, I would put a sum here on the left-hand side, justified interchange between the sum and this complex integral, and then sum over n, this guy here, and this Bessel function here. I will put the things. So if I want to recover their formula, note that I knew k nu, I just need to use this integral. And let's see what we get. So I put the formula, I sum that I knew k nu, I put the sum inside of the integral, justifying, of course, appropriately that I can do that, but it's not very difficult to do because these gammas are quite nice. We have two gammas above and one gamma below. The decay is very nice due to Stirling's formula. And then I need to evaluate this sum. But this sum, we already met this sum. Let us recall from Watson's formula. Note that in this formula, which was a corollary of the formula of Bernd, Dixit, and co-authors, we have a Bessel function k nu multiplied by a power of n, and you have the same thing here. The only difference is one, is like, in this formula it is assumed that the real part of the power of n is greater than 0, and here we don't know. But note that, let us see the conditions of the integral again. C, so the real part of the argument of the integral, is between a negative number, minus 2, real part of nu is assumed to be positive at the beginning, and 1. So, in particular, it's valid when C is between minus 2 real part of nu and 0. I can assume C to be negative. And if it is not negative, assume that it is positive. I can shift line of integration in the Cauchy theorem. The function is analytic, so it's okay. I can shift always to when C is negative, when the real part of the argument S is negative. So, if the real part of the argument is negative, this means that this guy here above is positive. So I can apply this formula. Applying this formula, of course, with the substitutions, like this x becomes x minus y, this nu becomes s over 2, and this nu becomes minus s over 2. Note that there's no problem in turning nu to s over 2 because k minus nu and k nu are the same. So I can put this exactly in this template by replacing s over 2 by minus s over 2. Doing these substitutions and applying Watson's formula, which can be proved independently, is a formula from the 20s, we could get that formula automatically using just an integral representation which resembles an index transform, which will be the subject of the next slides. And using these kind of things, the same technique, we could prove several formulas that the other authors did not consider. For instance, involving products of MacDonald by MacDonald, modified Bessel function of the second kind by modified Bessel function of the second kind, and then by another Bessel functions and mixing the different Bessel functions. And in particular, you could get some new formulas like this. I ask here, like, does this formula look familiar? It is familiar because when you take y equals 0, we recover Watson formula again. But these kind of formulas are new in this sense. So in fact, using a kindly, slightly different argument, we could also prove, but I'm not going to show, you'll see why the formula, because it's very long, of a formula involving products of Bessel function, but with different indices. Note that in the formula of Bernd, I can show again, it's here, all the index of the Bessel function need to be the same. It's crucial. And in our formulas involving these mixed Bessel functions as well, the index needs to be the same. But you can take a variant of these kind of arguments to prove formulas when the index are not the same. But as I say here, and in fact there is a formula like that, a formula that they conjecture, Bernd, Dixit, and co-authors. But I now say, like, making an excuse a la Fermat, like the proof is very long to contain in these slides. The formula is very long to be contained in these slides. It's an excuse a la Fermat. So let me now, the proof, the simple proof that that I found used, I can show again the integral. Used an integral with respect, as you can see, with respect to S. So the integral, in fact, as a product of gammas, as this exponent, which is inoffensive actually. And then the main part of the integral is that it is with respect to the index of the MacDonald function. And these kind of things, these kind of integrals, are alike the Kontorovich-Lebedev transform. Why? Because I can fix a C, like C is between this guy and 1. You can fix C equals 0. And then rewrite this integral as an integral, as a real one. Right, like when S appears, you always write like S equals to minus IT, for instance. And then the integral becomes from minus infinity to infinity. Just changing variables. And if you do these kind of things, you take the integral that, the point of departure, and you make this change of variable, you'll get something like this. You get something of this type. Okay? You get a function multiplied by the McDonald function evaluated at whose index is purely imaginary. And this is usually how the Kontorovich-Lebedev transform is introduced. So taking the integral as a point of departure again, the previous integral, you take c equals 0, and you get this. So our way to prove the formula of Bernd and get new formulas was actually to take a Kontorovich-Lebedev transform as a point of departure. Like we have the modified Bessel function here, we have an integral with respect to the index, and then you have this function that you need to calculate the transform. But this was the point of departure. And then the next question was like, if I put a function here instead of this product of gammas and etc., if I put a function which has a number theoretical interest, like the Riemann-Zeta function, what can happen? In fact, what is the question? This is a question from 2022 actually, but we now connected with this different work. What is the Kontorovich-Lebedev transform of this function that we introduced at the beginning, which is real? Remember that due to the functional equation, this guy here assumes real values on the critical line, when the real part of S equals 1/2. So let us try to, this will be a real function when restricted to the line. Let us try to calculate the Kontorovich-Lebedev transform of this real function, okay? And we have a lemma somehow, which says that if you calculate the Kontorovich-Lebedev transform of this guy here, which has a number theoretical interest, you'll get this series. Of course, this result is mainly computational. It's like, it's technical in a sense. But using this kind of information, you can get new transformation formulas involving the modified Bessel function evaluated at 1/4. How? Note that this guy here is invariant if you replace t by minus t due to the functional equation. This guy here is also invariant and you replace t by minus t because it's a property of the McDonald function. K nu of z is always k minus nu of z. So if you replace t by minus t, it's okay, it's the same guy. But this one, if you replace t by minus t, it's the same as you replace xi by 1/xi, right? If you replace t by minus t, you get xi to the it. But this is the same as 1/xi to the power of minus it. So what does this say? This says that this thing here is somewhat invariant when I replace xi by 1/xi due to the symmetries of this integral. And this gives a new summation. Note that we have an invariance in these both cases. The only thing that changes on the left-hand side and right-hand side is the xi. Below, it becomes 1/xi, and above it becomes xi. So we can get, this formalism works not only for the Riemann-Zeta function, for any Dirichlet series. You can get a lot of new formulas just by looking at the Kontorovich-Lebedev transform. This is one of many examples. And now I will introduce somehow the last part of the talk, which says the following. Note that in the beginning, motivated by something about zeros, I won't describe that, a technical thing of number theory, we were mainly interested about sums of products of Bessel functions, but with respect to the argument. Note that the variable of summation is exactly the argument of the Bessel functions. But the same question can be asked, what about if the argument of the Bessel functions is fixed, like the index is here, but the variable of summation is the index? That's the question. What can we say about sums of this kind? Like the sum now is not under the argument, with respect to the argument x and y are fixed now, x is fixed, but the variable of summation is precisely the index, I and alpha. What can we say? And there's a result due to Semyon. This does not work very well, but the reference is here. The reference is at the end. Sorry for that, cannot be read here. In my computer, it works just fine, but Semyon proved that if you take the sum of the Bessel function with respect to the index, you get this kind of transformation. He used Poisson summation formula and well-known Fourier transform of the Bessel function, and he could also do the same for products. now the formula becomes a little bit more complicated because it appears a k0 here, while here appears an exponential, an elementary function. But our question next was, can we do the same when we replace the Bessel function by a more general function, the Whittaker function, which actually appears in orthogonal polynomials? It is related with Laguerre polynomials and generalizes this function here. Can we do that? And the question is that we could do that. Let me just introduce the function in question. The Whittaker's function is usually introduced as this combination of confluent hypergeometric functions. But the thing is like we have to, in the case of the Bessel function, we have only one index. The thing that I want you to remember is that in the Whittaker function, you now have two indices. And if you fix one, mainly the first, and you set equals to 0, you recover the Bessel function. That's the only thing that I need you to know. And the question was, can we repeat? Let us look again to Simeon's formula. The formula is with respect to the index of k. Can we do the same with respect to the second index of the Whittaker? That's the question. Let us see. These are only properties of the Whittaker function. When we take the first argument equals to 0, you recover the Bessel function. And then we take the argument differed by 1/2, we get an elementary function. That's only basic properties. Okay. The question is, we have this reduction formula. And we have the formula from 2008 that Simeon proved using k, I, and alpha of x. The question is, can we prove something for the Whittaker? Note that such a formula will reduce to the formula that we know, because when you take mu equals 0, you can recover the formula obtained by Simeon. And in fact, we could prove this formula. Now that note that in the formula previously, with respect to the Macdonald function, what appeared at the right-hand side was an exponential, elementary function. Now we have a symmetry that appears a Whittaker function. And this is the main result. And note that as particular case, you can get this. By fixing mu equals 0, you can recover the formula from 2008. And the main idea of this formula, the main idea of the proof, was using this Fourier transform, which was actually the only way that we could compute that was by invoking this Mellin-Barnes representation, and then compute, if you want to compute the Fourier transform of the Whittaker function with respect to index, in a certain point you need to compute the Fourier transform of this product of gammas, but this is well known, and inverting everything, you could get the formula, which we could not track on the literature, but it's interesting, and there is another, there are other familiar formulas, cousins of this formula that you could get. For instance, we could get formulas with respect to index of products of Whittaker functions, and then products of gammas and the Whittaker function as well. But we don't know what we didn't address this case, like when the indices of the Whittaker functions are the same. We could get a formula when the first index and of both Whittakers are symmetric. We could get a formula for that. But in this case, is more difficult. It's much more technical. And another question that I would like to leave. Previously, I talked about the Kontorovich-Lebedev transform of the Riemann eta function, like the complete version of the Riemann zeta function. I could compute that. But can we do the same when we replace the Bessel function here by the Whittaker function? I don't know. It would be very nice to obtain a formula of that in that setting. Okay, me and Simon are very grateful for the invitation, of course. Pat really was a dear friend of us. So it's a pleasure to honor him in this conference. So it's okay. I don't know if Simon would like to okay. Expert comments now.
Thank you very much for your invitation. It's a bit great. It's indeed a great opportunity to pay tribute to our friend Zé Carlos. And I personally remember our numerous discussions about such kind of problems when I arrived to Portugal. And as you understand, we are representing our area of integral transforms and special functions. despite centuries old, is still active and developing many interesting classical things. And as you can see, this promising contribution of Pedro gives significance of, in particular, Kontorovich-Lebedev transform, which is indeed a basic transform of a new class, which I started to investigate early 80s. And then 86 years ago, it was introduced by two physicists, Kontorovich and Lebedev, relating to some problems in mathematical physics. At that time, it was just curiosity, really reciprocal formulas of new kind, which involves integration with respect to parameter of a Bessel function. Before the end of 19th century, Meller did similar stuff with spherical functions. It's kind of Meller, we call Meller-Fock transform. And then Kontorovich and Lebedev applied to mathematical physics, and then some around 50 years it was just time to time appeared in mathematical papers. And I got this problem to develop this kind of transformations with this nice kernel, you see, McDonald function of pure imaginary index. And then we understood that we can generalize this kernel because we know perfectly the structure of so-called hypergeometric functions. And this we come to the Mellin transform technique. As far as you, perhaps you know how it is good involved in a series of special hypergeometric functions, which is a structurally, its Mellin transform contains only the ratio of the product of gamma functions. This was a great demand of Wolfram Research Corporation, Mathematica, which we were involved in 80s to create algorithm to analytical calculation of integrals. And as you can now use Mathematica as users to do this, but it's still, they have a great demand to involve index transforms. At that time, we introduced this notion in 80s, index transform, because you understand of this integration by index. So my former supervisor is now working in Wolfram Research, so this is still contacting time to time, trying to involve these index kernels, which Mathematica doesn't know how to calculate such kind of integrals because there is no good algorithm, only general formulas we can involve, and this was done with our group in 90s, 80s, and later, involving Mayer G function, which is one of the more general special functions you can find on internet, really all information, necessary information. And then we proved, and also it started from American mathematician Wimp, he did formal proof of such reciprocal formulas involving G function, and I simplified these formulas, and we introduced this notion index transforms, which are now is worldwide used, and hopefully it will be more involved. And now you see the Pedro's contribution, very promising contribution to involve this in number theory, because 40 years ago I was criticized, why is this beautiful formula, where you can apply this? And now we have great applications, and we have more demand to use in number theory, because this classical group, starting from Ramanujan, centuries old results, and then Bernd, you know perfectly, I hope, 5 volumes book, Lost Ramanujan Notebook. We still are discovering very classical old formulas. We can give more fruits, more applications, more good, interesting results. And of course, I'm now working in we are interested in number theory questions, classical, of course, classical irrationality problems, and so on. And still discovering new index transform. What means discover new transform? How to give a life to a transformation. So it could be inverted. It could be inverted. It could be given a reciprocal inversion formula, concrete, explicit. Of course, we are studying involving functional analysis, LP spaces, L2, LP, Parseval equality, and so on. And then finally we come up with these great number theory problems, this infinite series involving Whittaker, Macdonald, Bessel functions. It seems for the first view quite technically complicated. But please compare what Ramanujan started and how great contribution he did, and still we develop such classical results. Then we come also to discrete class of index transform and still have interesting problems. Of course, it involves also approximation theory results. So we are trying to employ many general theory in approximation functional analysis to, of course, rigorously justify all our steps of proofs and so on. So it's not only formulas for computers, not only. So it's interesting theory, still developing, and hopefully we can succeed in some stuff very difficult in number theory, as far as you know, irrationality, transcendental problem, and so on. And I think it's our goal for near future, and of course such young mathematician as Pedro will continue, and also we will involve more people, more interested people in such topics. Thank you very much for your invitation.
Thanks very much to Pedro and Semyon. Is there any question or remark?
Sorry for the...
Is just to say that I have many questions, technical questions, but okay, the time is out. Let me just remark something. Pedro commented something regarding irrationality and Petronilo, and it's true. During the last 10 years of his life, we worked very hard without productions, without papers. Indeed, we studied very hard on the rationality of certifiers. And we have two run proof with two different approaches, and I still have in my hands the paper worked in LaTeX with the sentence that we cannot prove and that I cannot prove still. And it's just that we have two run proof and many hours of study in parallel with our work. So this is extremely nice topic. And Pedro and Jakubowicz are essentially, well, they are really good. Jakubowicz is the most fortunate people in Portugal. He has the best student in Portugal. Unfortunately, it's hard for his student obtain a position in Portugal. Yeah, the last one is in the private sectors, and we are very concerned regarding Pedro. That is extremely sad, but it's the reality in some places of the world. But Pedro and also the previous student and Jakubowicz are extremely good mathematicians. Thank you very much for your time.
Thank you.
Any other question or comment? So, congratulations for your nice work, and let's thank again. So let's continue. Our next, it's my pleasure to introduce our next speaker. It's Mohamed Amouch. Okay, and it's also a joint work, as you can see, and the title is Some Versions of Recurrence Property and Related Results. So,
thank you so much. I would like to thank the organizers of this event, namely Professor Paco and Professor Fernando, for their kind invitation. It is a great pleasure to be here between you and in San Luca. My talk is about some version of recurrence property and related results. This topic is related to interaction between operator theory and linear dynamical system. Let me begin with some tools about this notion of dynamic in operator theory. We will say that a dynamical system, which is given by space and the transformation, that this dynamical system, which consists of topological vector space and continuous map with X, will be the system, and the system can be biological, physical, or economic, like the talk of yesterday with dynamical system related to the biology. And the possible state in the system will be described the element of the whole space, and the evolution of the system will be described by the transformation. This theory studied the long-term behavior of evolving system. Operator in acting on a space X will be hypercyclic when his orbit is dense. That means that the iterate of T over X, which will Tn of X, when X is in this. X is dense in the space under the topology. And this notion is related to two areas. It's related to a problem of invariance of space, and it is related to ergodicity. Let me see, invariant subspace problem. Given a linear operator T on X, it is possible to find a non-trivial closed subspace invariant T which lack non-trivial invariant closed subspace. This is equivalent to the orbit is equal to X. And this notion also related to Poincaré problems, which assert that if you have a measurable space and a measure preserved in mu, which is strictly positive, then operator, the iteration dwell to the point. That means that if you take a measurable set A and a point in the space, that over iteration we can dwell to the set A. This a central concept in linear dynamics, which can be, with equivalent to this property, is topologically transitive. We will say that operator in T is topologically transitive if there exists a non-empty subsets U and V, such that we can dwell to V under in time. That means only that if we take open subsets U and V, that if we go from here at a moment, at time n, we meet or we dwell to V. This is equivalent to ergodicity. We say that a measurable map is ergodic if it is measurable, preserving, and satisfying one of the following conditions. If we take measurable set A and B, we can dwell from A to B at n time. And if we take a Brownian set A, which is invariant, then his measure is 1 or 0. By Bayer category, we can prove that the assertion that the orbit is dense is also equivalent to topologically transitive, but in Bayer space. Let's take a separable space and let a bounded linear operator T. The following are equivalent. Hypercyclic is equivalent to topologically transitive. We use this to prove some results, old results. For example, that the backward shift defined in a space L2, lambda of B is hypercyclic if and only if modulus of lambda is greater than 1. Now let me introduce another notion, is the recurrence. Recurrence which came from ergodicity. This study was old, and actually it is studied by Kostais, Manoussos, Parisis, and others mathematicians. Operator T acting on X is said to be recurrent if each non-empty set A of X, there exists a positive integer n such that U dwell to U. That means not like hypercyclicity here, that if we take a non-empty subset n and if we take a point, it dwell to the same, it dwell to the same open set after one time n. There exists n such that the n E intersect E. This is equivalent to the sequential form. There exists a sequence of positive integers such that the nk of x converge to x. That is, x is a limit point of the orbit. The set of all vector recurrent is denoted by rec t, and it is dense in x. If t is recurrent, then the set of his vector is dense in x. Now, we will introduce notion of supercyclicity, which asserts that not only the orbit which is dense, but the cone generated by the orbit is dense. And a result of Bayard, he gives the set of all vector cyclic by this intersection of here open set, which is a G delta set. We have a particular way to prove that an operator is supercyclic. It is Birkhoff. This way is the supercyclicity criterion, which asserts that T is supercyclic equivalent to do a property-like transitivity theorem with a constant lambda and the subset of supercyclic vector is dense. By this characterization, we can prove that for a bounded sequence with weight Wn, which is not null, and in canonical basis, the shift here is supercyclic, and if this sequence goes to 0, then the set is supercyclic and can be compact or quasi-nilpotent. From this, we see that it is clear here that we have, if we have recurrence, if we have hypercyclicity, then we have between them, we can introduce a very important class of operator called super-recurrent, which is strictly included in a recurrence and contains strictly super-recurrence operator. We say that T is super-recurrent if every non-open subset did exist N such that this quantity is not empty. And we prove first that a vector X in X is called super-recurrent vector for T if there exists a strictly increasing sequence of positive integer and the sequence lambda n of complex number such that X as a limit point of the cone generated by the orbit. We will denote S recurrent of T the set of four super-recurrent vectors. The first remark is to see that the supercyclicity implies the super-recurrence, but the converse is not true. We can consider operator T from Cn to Cn with coefficient lambda 1, which lambda 1 modulus lambda E, lambda G is equal to R, with R a positive real number. Then we can see that T is super-recurrent operator. However, T cannot be supercyclic whenever N is greater than 1. Since a Banach space X, this is a result. Support supercyclic operator if only F, his dimension is 1 or empty. Remark 2, a recurrence vector is super-recurrent, but the converse does not hold in general. If we take the same operator, then this operator is super-recurrent. However, it is recurrent if and only if modulus of lambda E is 1. Now, we will give some property established for this notion, for this operator which are super-recurrent. We give some property here. If S is operator in B of X, such that it commutes with S, with T, with an operator T, then the set of super-recurrent vector is invariant under S. And we can see that this important result, algebraic important result, holds that if P is a polynomial of Z and T in B dx, then P of T, which is equal to this sum, is P of T of X when P is this polynomial is included in super-recurrent vector. In particular, if T has a super-recurrent vector, then it admits an invariant subspace consisting, except 0, of super-recurrent vector. That means that we delete 0 from the polynomial of T applied to X. If T is super-recurrent operator, then it is of dense range. His range is dense. And if we take, we will define here conjugancy between two systems. Two dynamical systems will be side to be conjugate when we can find a transformation between them which is with dense range, and we say that are similar when this transformation is homeomorphism. If T and S are operator acting on X and Y respectively, then S are called conjugates or quasi similar if there exists some phi with dense range such that S of phi is equal to phi of T. If can be chosen to be homeomorphism, then T is called similar. Alors, we prove that if T and S are operator T in X and S in Y are quasi similar, then T is super recurrent in X, imply that S is super recurrent in Y. Assume that T is operator in T and S in Y are similar, then T is super recurrent in X if and only if S is super recurrent in Y. Now, we will give some characterization for the weighted shift in LP. We consider weighted shift LP space. In order to give this characterization, we will need a lemma. We take LP space with here weight mu and T if T is operator in BDX and T is super recurrent, then we have this assertion. That means that if there exists a sequence of element in X and the sequence lambda n of complex number, and then X can be the limit of xk and X can be the limit of lambda nk take. It means that X is a limit point of the cone. This lemma will help us to prove the following theorem, which is a characterization for the shift. Let be a bilateral backward shift in LP or C0, then B is super recurrent if and only if for all L in Z there exists a sequence of non-negative integer nk and a sequence of non-complex number lambda k such that this limit goes to 0 and this limit goes also to 0. 1 over lambda k multiplied by the weight and lambda k multiplied by the weight are also 0. The characterization is this. Let be a bilateral backward shift acting on LP or C0. The operator B is super recurrent if and only if it is supercyclic. That means that for this backward shift, recurrence and supercyclicity are the same. Now, we can generalize this to the backward shift with weight. If we take Wnk as a weight of this backward shift B of WA, then B of WA is super recurrent if and only if BWA is supercyclic. Now, I will speak about another notion which is studied now by a number of mathematicians, namely Costais, Alfredo Perez, and others. This notion is topologically transitive. We do not consider only one open set, but a product of open set. Operator T acting on X is called topologically multiply recurrent operator if every non-open subset U of X and every non-integer M there exists a positive integer N such that U intersect T minus N U, T minus M N U is not empty. If M is 1, then this property is recurrence. So if T is topologically transitive, then it is recurrence. What our work consists to prove some results for the shift, to see the shift topologically transitive if it is also, which is recurrent, is also topologically transitive. If M is 1, then the recurrence, the topologically transitive is recurrent. We take this example, the subset example demonstrates that the converse does not hold. If we take T in L2 to L2 of Z bilateral backward shift, we'd wait to if N is greater than 0 and N over 1 plus if N is greater than 0, here less than 0. T is recurrent but not topologically multiply recurrent. This operator is recurrent but not topologically multiply recurrent. Here we give a characterization of topologically multiply recurrent. First we give a characterization and we deduce the result for the shift. We can deduce the result for the shift. If we take T operator that act on a free space, then T is topologically multiply recurrent if and only if for every M and X there exists a sequence of vector X and strictly increasing sequence of positive integer N, okay, such that for every L we have K, the sequence XK goes to K and T ln K of XK goes to X as K goes to NFT. This characterization led us to give a characterization for the shift. The future work for this will take in account the generalized backward shift and to try to give characterization for the shift operator between all property of dynamical system. As you know, this aim of research is related to differential equation because there is a relation between this and the study of behavior of the solution of the equation. In an ODE, the solution is just orbit. Algebraically is orbit, and geometrically is a parameterized curve. And to study the behavior of the orbit is also to study the trajectory or the parameterized curve as a solution of the equation. Here we have some reference. Thank you so much.
So thanks for your talk. Is there any question or remark?
Thank you for an interesting talk. When you have these operators S and T, which are related by the intertwining equality, they are super recurrent simultaneously. And my question is if the sequences of the numbers which are involved in the definition of super recurrent operators, they are the same for them in this case, or not necessarily?
Not necessarily the same. No, they are not the same.
Okay.
Like we go from a system to a system. If you go from a system to a system, if there is homeomorphism, we can get the inverse of the states. Other you cannot accept anything.
Mm-hmm. But can you compute the sequence of the second one if you know the sequence for the first one?
Yes.
Yes, you can compute.
You can, yes.
Okay.
Normally, when we work with the concrete operator, with abstract operator, I think if the transformation is Homeomorphism, we can describe it in the case of abstract operator T and T. When we have operators, concrete operators, we can deduce the states.
Okay, thank you.
Thanks. Any other question or remark?
Okay, so you define the recurrence and the super recurrence, but it looks like the recurrence is stronger than the super recurrence, right?
If you have recurrence is just you take U, we can dwell to do sit. This is recurrence, but here we can dwell with in the cone. This we have the cone generated by lambda, complex number.
Yeah, so that's why, because you
If
have...
lambda is 1, we can yes.
Yeah, so that's what you said, that recurrent is stronger than super recurrent.
Yes.
So why do you use the name super? Because it's a little bit misleading. It's should be sub recurrent.
Yes. It was a long story with this name to name it super recurrence. And the first, the referee told us to change the name. But the paper is shared and it is in archive, and we said we work with this and we refer in the other papers to this name. And
it's not your fault.
There is a problem with the name. Yes, okay, thank you.
Okay, also you said that they're equivalent if, because you wrote the modulus of the lambda I equals to 1. Should it be just lambda I to be equal to 1? Because in a definition, you don't put modulus on lambda I, you just use lambda I, right? You said the recurrence and the super recurrence are equivalent when the modulus of lambda I is equal to 1, but shouldn't be just lambda I equals to 1.
No, this is just an example to give the first implication. If lambda is 1, is just a particular case.
But if just a modulus, are they still equivalent?
Modulus, yes.
Thank you. Okay.
Thank you. Any other question or remark? No? So thanks a lot for your nice talk. Okay, so I was told to be on the stage for the light because of the light. So it is my pleasure to present to you our next speaker, Tatiana Andreeva. And the title of her talk is The Surjectivity and Injectivity of Convolution Operators, Some Interdisciplinary Corollaries. I'm sorry.
Well, dear colleagues, it's a great honor and pleasure for me to present my today's talk devoted to convolution operators defined on special weighted functional spaces. These spaces are constructed as follows. First of all, suppose that G is a bounded convex domain in complex plane that contains origin. Denote by H from G the space of all functions that are holomorphic in G. Let us consider an auxiliary sequence phi. There's something with sound, I think. Let us consider an auxiliary sequence of phi of some positive convex monotonically increasing function satisfying the following three conditions. These conditions are similar by those used by Nabelkov, with the only difference that Nabelkov constructed the space endowed by projective limit topology, and we use the inductive limits. The first and the second one are just natural. They imply the connectivity of differentiation, and the third one has a technical character and does not put any strong restrictions. Further, let weight Vn be the function phi n from an argument logarithm 1 divided by distance from a point of a domain to the boundary of this domain. Thus, we define the main weight sequence V. To each weight Vn, we assign the following Banach space of holomorphic functions Hn, and let Vh from G be the inductive limit of this space sequence. Vh is our main weight space. Further, suppose mu is an analytical functional in C carried by a convex compact set K, and consider the convolution operator. It is a well-known fact that it maps continuously the space of functions holomorphic in G plus K into the space of functions holomorphic in G, and also consider the corresponding non-homogeneous convolution equation 1.1, where the solution is from the space of functions holomorphic in G plus K, and the right part from from G. Now consider the same operator defined on the weight space VH G plus K and mapping into or onto VH from G. Speaking about continuity, we use into. Speaking about surjectivity, we use onto. The questions of this talk are: when the convolution operator continuous or surjective? When does the non-homogeneous convolution equation have the unique solution? The result for a convolution operator are given in terms of its analytical symbol, the Laplace transform of the functional. Let us recall that for any functional mu, its Laplace transform is given by hatchet mu from zeta. It's an entire function of exponential type satisfying the following condition of growth at infinity. Here, hk is the subpart function of the compact K. To obtain the surjectivity criteria for the convolution operator in terms of its Laplace transform, we have to consider particular cases of weight sequence V. We consider in this talk the space of exponential power growth and normal type defined by the following weight sequence Vn. Also, let us recall some useful definitions. Let phi be an entire function of exponential type. Its radial indicator is defined as follows. We use the multidimensional definition radial indicator instead of a classical indicator just to simplify the proof, just only for these purposes. For each analytical functional mu with the defined properties, the radial indicator of its symbol is less or equal than the subpart function hk. And the first of the restrictions on symbol is the equality instead of inequality here. The second restriction is the complete regal growth condition. Namely, we will say that the entire function phi of exponential type satisfies the S alpha condition of growth if for every point zeta sufficiently far from the origin, there exists zeta prime from a rather small neighborhood of zeta in which the function phi satisfies the following lower estimation. Please note that this condition is stronger than the completely regular growth condition. Finally, we're about to present the main result of this talk, the surjectivity criterion. Suppose mu is analytical functional in complex plane carried by a convex compact set K. Hatted mu is from the auxiliary space VH infinity of the entire functions. Then the convolution operator is surjective for every bounded convex domain G if and only if the radial indicator of its symbol is equal to HK, the support function of K, and hatted mu satisfies the condition as alpha of regular growth. Further, let us consider the non-homogeneous convolution equation 3.1, where the solution is from our weighted space VH G plus K, and the right part is from the weighted space VH from G. Suppose, furthermore, that mu is surjective. It's a well-known fact that the convolution operator is injective if it has a non-zero symbol in G. The question is, can the equation have a unique solution otherwise? One of the answers is, let D be a neighborhood of origin such that its closure is embedded into our domain G. Let D contain the finite number of zeros of the symbol hatted mu, and let M be a number of zeros of the symbol of mu hatted in D, taking into account their multiplicity. We consider the Cauchy problem 3.2, 3.3. And then, for each right part from VH from D, not from G but from D, there exists a unique solution from VH from D. It's one of the answers. Let us consider another application. It is interesting to consider convolution for with some particular operators. For instance, within the subject on fractional integral differentiation. One of the models within the framework of fractional integral differentiation is the Riesz integral differentiation. And Riesz potentials fulfills the negative fractional degrees of Laplace operator, acting on the space of functions of many real variables. The Riesz potentials seem to be interesting to extend them on the case of complex analysis, and such an attempt is made here. Let us consider mu, an analytical functional that is defined by the measure psi d lambda. Lambda is Lebesgue measure here, and assume that it has the following Laplace transform, a function m from an argument zeta. The inverse Fourier Laplace transform of psi considered as a function of two real variables is the following function, and it is an analytical function of two complex variables. Though we consider the functional mu such that there is the correlation between the defining function psi and the symbol m. Here it is. Now let us recall the Fourier transform and inverse Fourier transform of an ordinary function phi, and also the translation property of on a vector x null fixed in R2. In Riesz analysis, the Fourier transform of a radial function is of great interest, and generally speaking, the Fourier transform of a radial function is a Fourier transform of a generalist function from the class of Schwarz functions. But in this particular range of the parameter alpha, the Fourier transform of a radial function can be computed as a Fourier transform of a normal, ordinary function via the Bochner's formula. And we get this following equation. Roughly speaking, the Fourier transform of radial function is also a radial function, but from another degree. And the right part here is the risk kernel K alpha. Here it is. The convolution with this risk kernel fulfills the negative fractional degrees of Laplacian, being an operator acting on a class of functions of real variables. Moreover, we need not only a functional that is somehow connected with risk kernel, we need functional mu with rather good properties, for example, with non-zero symbols. And to guarantee this, we should guarantee the translation property. Please see this framed expression. This expression can guarantee that the Fourier image of a radial function satisfies this translation property. And thus, we can calculate the symbol of mu, m out from zeta, as a function in this exact form, from an argument zeta complex and parameter zeta that is also complex. It uniquely defines the functional, which we suggest to consider as Rees potential type operator. And finally, under the corresponding conditions of the presented theorems, the convolution with the Rees potential type operator mu defined by M is surjective or bijective, is defined from the concrete theorem in the spaces of Lamarckian functions of preset growth. So, I'll skip this. That's the end of my part. It's not working, but I can hear it.
Thank you. Oh, gracias. You have a question? No?
Excuse me, what you can say about the Bessel potential? Bessel potentials, because it's quite nice generalization. Rees potential. So it's the same book of Samko, you can see this. Did you study it?
I haven't considered that.
Because it's involved Macdonald functions and very nice behavior. It's similar to Rees potential.
You know, it's rather new result, so I haven't worked.
It could be a good project, I think, to apply your theory to Bessel potentials.
Thank you for this idea.
Thank you. Any other question or remark? So I will thank you in two ways for your very nice talk, and you enable us to gain some time, so it's not usual. So thanks again. sorry for the small. It is my pleasure to introduce our next speaker, Giuseppina Gerarda Barbieri, the University of Salerno. And the title of her talk is From Sets to S Sets. So, please.
Everybody, first of all, I would like to thank the organizing committee for giving me this opportunity. And the title is From Sets to S Sets, but maybe the title should be The Fundamental Theorem of Calculus Integral Line to the History. Okay, the theorem, very well known, is this, contained also in the book by Cauchy, written in 1831, the first version. And okay, if f is differentiable of an interval, then the definite integral of its derivative equals this difference. And it is very, okay, I must approach the microphone. And it is also very well known that in the case of Riemann integration, it is necessary to add the additional condition that the function must be Riemann integrable. This condition is necessary because not every derivative turns out to be Riemann integrable. And here is a well-known example of a function which is differentiable everywhere on the real unit interval, but its derivative is not Riemann integrable since it is unbounded, and it is neither Lebesgue integrable since f is not absolutely continuous on the real unit interval. Therefore, as it is well known, the Lebesgue integral as well as the Riemann integral does not solve the problem of primitives. Well, the problem of primitives is the problem of recovering the function from its derivative. It has the problem of whether every derivative is integrable. And as it is also well known, the Lebesgue integral solved the problem of primitives in the frame of bounding function, but it does not completely solve the problem of primitives for unbounded function, and the previous example has been done by Lebesgue himself. But the history continues, and the first solution to this problem was given 10 years after Lebesgue's thesis by Arnaud Denjoy in 1912, and he was followed by Oscar Perron in 1940, who was inspired by a characterization of the Lebesgue integral function given by Charles-Jean Barrault de la Volée-Husson. Both definitions are constructive. Denjoy developed a very, very complicated new method of integration called totalization that includes the Lebesgue integral and that gets the value of the integral of a function through a transfinite process of Lebesgue integration, limit operation, very, very complicated. Perron used instead an approach that does not require measure theory, and it is based on families of major and minor functions, the so-called overfunction and underfunctions. And later on, Hayek, Alexandrov, Luhmann independently proved that the Denjoy integral and the Perron integral are equivalent, and indeed now it is called the integral of Denjoy-Perron. But only using make this definition understandable, and he introduced the following notion of absolutely continuous in the strict sense, AC star, and generalized absolutely continuous in the strict sense. And this definition is based on the oscillation, which is supreme. Okay, we can read a function is said to be absolutely continuous if the sum of oscillations is smaller for each finite system of non-enveloping intervals with these two properties. and a function is said to be generalized absolutely continuous on an interval if it is continuous and there is a decomposition of the original interval as the union of closed sets such that the restriction of f to ei for each I is absolutely continuous in the strict sense. And okay, so Lucy was able to prove the following characterization of the Danjois-Perron integrable function. A function is Danjois-Perron integrable if and only if there is another function, capital F, which is generalized absolutely continuous in the strict sense on the interval, which is differentiable almost everywhere for Lebesgue measures on this interval, and such that derivative coincide with the original function almost everywhere on the interval. Okay, just two remarks. The if part of this characterization is often called the descriptive definition of the Danjois-Perron integral, and since the constructive definition of the Danjois-Perron integral was not immediate as that of the Riemann integral, only a few mathematicians were interested in working with it. So this descriptive definition became the most known definition of the Danjois-Perron integral. And another remark, in contrast to the Riemann and Lebesgue cases, if f is the Danjois-Perron integrable over interval, its absolute value needs not to be the Danjois-Perron integrable. The Lebesgue integrable functions are exactly the ones which are Danjois-Perron integrable together with the absolute value. Okay, so in spite of the general conviction that no modification of Riemann method could possibly give such powerful result as that of Lebesgue integral, Kurzweil and Anstok introduced independently a general version of the Riemann integral that now is known as the Anstok-Kurzweil integral, and such an integral solves the problem of primitives and includes the Lebesgue integral, of course, in the sense that if a function is Lebesgue integrable, it is also integrable in the sense of Anstok-Kurzweil, and the two integrals coincide. Okay, and now we are going to give the exact definitions of Anstok-Kurzweil integral. We need as an ingredient a gauge. A gauge is simply any positive function defined on an interval. We need a tagged partition, which is any collection of pairwise disjoint intervals with points arbitrarily chosen inside AI, such that the intervals is the union, and the key ingredient. The key ingredient is a delta affine partition. Too high. Okay, is delta affine partition whenever P is said to be delta affine, whenever AI is contained in this interval xi minus delta xi, xi plus delta xi for every I. And the last ingredient is the Riemann sum of f with respect to partition, which is defined in this way, where lambda is the Lebesgue measure. Okay, yes, a remark. Given any positive constant delta, it is always possible to construct a tagged partition which is delta affine, or as mesh size smaller or equal to delta. But in the case of an arbitrary non-constant gauge, delta, the question is more delicate, and the existence of delta affine tagged partition has to be proved. And this was already done in 1895 by Pierre Cousin, and here is the Cousin's lemma, which is equivalent to the classical Borel-Lebesgue property. Okay, and now the exact definition of Kurzweil integrable function. Okay, a function is said to be Kurzweil integrable if it is possible to approximate the number. The integral with delta fine partition P. And okay, this number I, real number I, is called Kurzweil integral on AB. It is denoted by this symbol HK, stands for Kurzweil. Okay, yeah, other remark, easy remark. The restriction of the Kurzweil definition to constant gauges just give the Riemann integral. The fundamental idea in their definition is to force the step to be smaller around points where the function is discontinuous or tends to infinity. And this idea, which is familiar to numerical analysts, was already mentioned by Euler. And this is contained in a very beautiful paper by Jean Moulin, to history of integration theory, Riemannesque versus Romanesque. And here is what Euler wrote in 1768. We can read these lines. Okay, we already have noticed that the intervals aj minus aj minus 1, that x is assumed to go true, must be taken very small in such a way the corresponding values f on aj minus 1 and f on aj do not differ too much one from the other. From this, one must decide if the intervals must be taken equal or unequal. Indeed, where the value of fx does not change too much when x varies, the interval in which x moves can be taken larger without danger. On the other hand, in places where small changes of x lead to violent variation of fx, one will have to take the interval very small. Okay. Well, yeah, the Kurzweil integral is equivalent to the Draper integral, and this result was shown by several mathematicians by proving the following characterization of the Kurzweil primitives. The family of all Kurzweil primitives coincide with the class of generalized absolutely continuous function, as used in proof. The Kurzweil definition has been adopted to introduce integral calculus in many monographs, and it is taught to undergraduate students in mathematics and physics sometimes. In Italy, I don't know in other countries. Okay. But now we come to assets, where an asset is for us a subset of the real line whenever the S-dimensional exterior Hausdorff measure is, which is defined in that way, supremum of infimum of these countable sums to the power of S, whenever E is included in this countable union with diameter less than delta, and S is strictly greater than 0 and strictly less than 1. This is actually a measure of Borel sets. And okay, so from now on, E is a closed set, and we have to generalize to this setting, which is an interval. An interval is simply an intersection of the classical interval with this closed set, and a tagged partition now is a finite collection of pairwise disjoint E intervals tilde I and point xi inside these E intervals. Okay, we have to generalize to this setting, to this framework, the Riemann sum, and we have the notion of S Riemann sum related to a partition P, but it simply substitutes the Labelle measure with these S Hausdorff measure. And of course, the intervals with these E intervals, and xi inside these E intervals. In this way, we can give this notion of S-Riemann interval, which is, okay, we can read a number. If there is a real number I, such that for every epsilon there is a delta, such that this difference is more for each partition, such that the S exterior out of measure is more than delta, and the number I is called S-Riemann integral of F1E. Incidentally, there are a huge literature on these S-Riemann interval. Scholars like Chinese scholars Jiang Su and Indians scholars like Parvati Jangar introduced an extension of the Riemann integral, which is up to a constant exactly this S-Riemann integral. And okay, and now we need also a derivative in this setting, S derivatives, and we use a definition introduced by three Spanish men, three Miguel de Guzman, Miguel Martin, Miguel Reyes. And here is definition of left derivatives and right derivatives as the limit from the right and from the left of the incremental ratio. And the novel is that the xx0 is defined thanks to S as of measure. And okay, as usual, we say that the S derivative exists if the left derivatives and right derivatives coincide, and here is the paper by de Guzman, Martin, Reyes, published in 1990. Okay, but now our aim is to look for the best version of an integral in this setting for the fundamental theorem for solve the problem of primitives. And S-Riemann integral is not a right integral because we have an example of a function defined on the ternary counter set such that its derivative, S derivative, where S is the dimension of a counter set logarithm of 2 to the base of 3, is a null function, so the S-Riemann integral is null, but of course this difference f on 1 is 1, so 1. It does not solve, does not hold the fundamental theorem of calculus. And hence, a generalized an extension of a Kurzweil integral on this setting to this setting can be done, and of course, exactly as in the classical case, we can we say that the function is Kurzweil interval if we can approximate with the delta affine partition now with elements are intervals. Okay, the peculiarity of the SH integral with respect to S-Riemann integral is that, of course, the SH integral allows to neglect the value of the S-Riemann sum related to some partition containing big intervals in proximity of very bad points. Okay, here is the comparison, of course. We have, for S-Riemann integral, involves S-Riemann sum related to partition whenever HS, the S exterior house of measures, is less than delta for some appropriate constant. Instead, for SHA integrals, involves the S-Riemann sum related to all partitions satisfying this inequality where there is delta on X-side gauge for some appropriate gauge, and okay, and a choice of X-side inside E intervals. Okay, another remark. If f is an SH interval function, but it is not S-Riemann interval, then of course this infimum must be 0 for each gauge. Otherwise, by way of contradiction, if we have that infimum equals delta, then that delta does the work in order to for baying f S-Riemann integrable. Oh, okay, simply remark. Okay, and now our aim to solve the problem of primitives for S sets. We had an idea. The idea was what happens? What does it happen if we use an integral in which the gauge is a positive constant, which is easier to handle, but the choice of points is not arbitrary in the interval, say I, but must satisfy some constraints. And to define this quite general integral, we adapt an idea from, by Dorji and Evans for function defined on ST. And okay, so consider a countable dense subset gamma of V. We call this countable dense subset a trajectory. Restrict our attention only to the S-Riemann sum related to all partitions such that S out of measure is less than delta for some appropriate constant, but such that xi is not arbitrarily chosen inside tilde ai, but is the first element of gamma that belongs to tilde ai for every I. Okay, the idea of first return type goes back to Poincaré's first return map of differentiable dynamics. It was already used in differential theory and integration theory, and I mentioned two papers by Malay, published in 1992, and by Freiling, appeared in 2000. Okay, yes, here it is the exact definition of our S first return integrable function with respect to trajectory, where trajectory is any sequence of distinct points of the S closed set density. And okay, we approximate with the partition such that the S out of measure is less than delta, and xi, as said before, is the first element of gamma that belongs to tilde I. Okay, we have some result. The S first return integral includes the Lebesgue integral with respect to the S out of measure. There exists a non-S Riemann integrable function which is not S first return integrable, but this idea, okay, I would like to skip for the last slide. Our idea to find the best version of integral in this framework in order to solve the problems of primitives. Integration is a reverse operation with respect to differentiation, is a bad idea because we find a function which is an S derivative, but f is not S first return integrable. So our attempt is a failure in some sense, and we can say that since there are S derivatives not S first return integrable, we can conclude that in order to obtain the best version of the fundamental theorem of calculus on S sets, exactly as in the real line in the classical case, we need to consider Ernst-Kurzweil type integral. It has an integral in which the gauge is not a constant. And these results are contained in a recent paper written jointly with my friend Donatella Bongiorno from University of Palermo and Alireza Khalili Golmakane from Iran. Okay, many thanks for your listening. That's all.
Thank you very much. Questions, remarks?
Thank you. And, my question is if there are some additional problems in a multidimensional case. For example, what's going on with Stokes theorem, Gauss theorem? So you always talked about the one-dimensional situation. Yeah. If there are some results in the multidimensional. Okay, thank you.
Thank you. Any other question or remark?
Thank you. Are there still problems that you cannot solve, and what could be the next step in generalization? Thank you.
As a disclaimer, okay. Yeah, as a disclaimer, this is not exactly my research topic. My friend involved me in this research topic, and we studied this aspect. Maybe, yes, there are many questions that can be developed in this field. Okay, yes.
Thanks. Any other question, comment? I must say the same thing, that thanks in two ways: for the time that you gave and for your very nice talk. Thank you. Now it's coffee break. I think it's it's no, but
Идите ко мне. Идите ко мне. И еще вот так вот.
usted está en percepción y los otros dos están en imagen y los otros comparten. Se habla de sí, no, ahora es posible que después se pasa el tiempo y vamos a ver una cosa, tío, acordarse es que si os ponéis aquí es que no se ve la cámara y os tenéis que poner aquí para que se vea la cámara y después si no te pega no se oye. Estamos por tiempo de tratar haciendo la pina y se le olvidaba.
A ver, que igualmente puedes hacer así. Me voy llevando el micro y vas hablando en plan por el escenario o lo que sea, ¿sabes?
Audio Jungle. So got it. Do you hear me?
So, good morning again. We should start this session. Before introducing the first speaker, I have some recommendations from the technical staff for all speakers of this session. Please be here above the light. So, Dieudonné, please, the first one. When talking, please do not give back. because of us, but also because of those that are at home. Okay, we don't remember this, but at the end it is fine to be aware of this. And speak close to the microphone and above the light. Okay, Dieudonné? And so it is my pleasure now to introduce the first speaker of this session, is Professor Dieudonné Buna. Dieudonné Buna, no professor, from the University of Seville in Spain. So Dieudonné, you have here, the talk is about the characterization of some classical and semi-classical orthogonal polynomials on lattices. So the floor is yours, please.
Thanks for giving me the floor, and I would like to thank the organizer for giving me this opportunity to speak. And it is a pleasure for me to be here because I was the second and the last PhD student of Professor José Carlos Petronilo. And that's why during this talk I decided to present some last results that we were working on. And unfortunately, he could not get see this work published before passing away, and yeah, that is very sad. So, before starting the presentation, I would like to share with you our first contact. It was at the end of 2016 when I arrived at the University of Coimbra, and because of the visas problem, and arrived almost at the end of the first semester. And directly after that, I discovered that there was a course on orthogonal polynomials in the program, and that course was supposed to be to held in the second semester. And I sent him an email saying that I would like to, if possible, to do my PhD studies on that. And immediately, he responded positively to my email, and during the first contact, his first question to me was, do you know the mathematician Jean Dieudonné? I said no, but he said that, oh, because maybe you can be, maybe you are one of his family members, but it was a joke. Yeah, so during this talk, what we are going to do, sorry. So what we are going to do is to start with the definition of an orthogonal polynomial sequence. So we suppose that we have a simple set of polynomial called Pn. We said that it is an orthogonal polynomial sequence with respect to an element in the dual base if there exists a non-zero complex sequence that we are going to call here Hn, such that whenever we apply U to the product Pn Pk, we always have Hn times the Kronecker symbol delta at n and k. We also say that the functional U is regular. So it is well known that orthogonal polynomial sequences satisfy a three-term recurrence relations where we have two coefficients in the relations, as you can see, Bn's and Cn's, with Bn's complex sequences and Cn's are non-zero complex sequences. If you are in the case of positive, definitive, or orthogonal polynomial sequence, it is required that Bn's are real and Cn's are positive. And in that case, we say that it is positive, definite with respect, it is defined, it is regular with respect to a positive measure. So what we call lattice here is this mapping where we have two expressions. The first expression with Q different from 1 is the Q quadratic lattice when we assume that C1, C2 is different from 0. And the second one when the Q equals to 1 is called the quadratic lattice when C4 is different from 0. And we define also two sequences, alpha n and gamma n, that you are going to see a lot during this presentation. And after that, we are going to define two operators called dx and xx in the space of polynomial, and by transposition, we will define the corresponding operator in the dual space. So that is what we are going to do here. Dx, xx, and in the dual space, that's how we define them. So, what we call classical orthogonal polynomials here, like we are in the space, we are considering that we are talking about the theory of orthogonal polynomials on lattices. So we say that a regular functional is classical if it satisfies these Pearson type equations, where the polynomial phi and psi are of degree 2 and 1, at most 2 and 1 respectively. So here we are going to give some characterization of this type of polynomials. So the first one that we call C1 is the definition that we just saw, like if you have a regular functional, then if there exists two polynomial phi and psi, so that the Pearson equation holds with degrees and most 2 and 1 respectively, we have a classical. And the second one is that the sequence of derivative with respect to the operator dx is also an orthogonal polynomial sequence. This is the hand characterization. And the third one is that each element of the sequence Sx of pi n can be always written as a linear combination of 3 consecutive terms of the derivative sequence, being the last coefficient be different from 0. The fourth one is that we can always find two polynomials, phi and psi, such that this second order difference equation holds. And this is the Bodner type characterization. And there are many other characterizations, and we would like to mention that these characterizations are due to several authors, but there is one paper where the authors try to prove all these equivalence at once, but we found that there are some mistakes in the paper. And so what we did, our contribution was in this situ where we prove something more than this. It was the synonym hand problem. Like if this problem was posed by Ismael in his monogram of 2005, and the problem was the following. If you have an orthogonal polynomial sequence Pn, if for some fixed k, the sequence dk of pi n is also an orthogonal polynomial sequence, then we have a classical orthogonal polynomial sequence, and that is what we proved. This one was a result proof with Kenya, and this characterization C3 was proved by Marcelin and Roberto Costa, and this one C4 was proved by Murad Ismail. Yes. Now, this is our fundamental question. We suppose that we have a non-zero functional satisfying the Pearson equations where we wrote the expression for polynomial phi and psi. We would like to know what are the necessary and sufficient conditions only based on these parameters A, B, C, D, and E, such that we guarantee the existence of an orthogonal polynomial sequence. And we were able to answer this question. That is, we need a sequence Dn and the other sequence phi n of C3 minus En over D2n, both different from 0. And here we define those sequences in terms of A, B, C, D, E, and also the sequence alpha n and gamma n that we define. After this, so when we suppose that this condition holds, we now know that all sequences of derivatives with respect to the operator dx are also orthogonal polynomial sequences. And so in this last work, what we did is to give the coefficients of the 3-term recurrence relation of all those sequences of derivatives with respect to the operator dx. Now, the proof is the following picture. And this picture was taken in 2000, near the end of 2019 by Renato during his visit at the University of Coimbra, and that is the period where we were working on this, and you can see on the blackboard some kind of introduction to this, and we share many things together, and that's how when we were working on this. So what are the related families? And it was shown that up to an affine transformation of the variable, the related orthogonal polynomial sequences are the Askew-Wilson polynomials, including specific and limiting cases. And here we provide the coefficient Bn and Cn for the three-term recurrence relation of that polynomials, but we would like to add that there are several cases of this polynomial in the literature. And why? That is because orthogonal polynomials, and in fact the classical one, appear in very different form in the literature. And that is why during this work we try to unify all this in a single theory. That's what we did. So you have, for example, the Curacar, the continuous dual hand, and so on. And so what we are going to do now is to move to a second conjecture that we solved, and this conjecture was also made by Ismail in his monogram of 2005, where he said that if you have a polynomial of degree at most 2, that we prefer to write here as az squared plus bz plus c, such that this structure relation holds, then the related orthogonal polynomial sequence Pn satisfying this are the continuous Jacobi polynomials or the Alsalam-Char polynomials, including specific and limiting cases. And we were very interested to solve this problem because this equation is well known in the theory of orthogonal polynomial, I mean the theory of classical ones, because if you replace the dx operator by the standard derivative, I mean d over dx, then you have a full characterization of what we call a classical orthogonal polynomial with respect to a continuous variable. I mean the Hermite, the Laguerre, the Bessel, and the Jacobi polynomials. If you replace the operator dx here by the Q-Jackson operator, dq, or even the Han operator, dq omega, up to an affine transformation of the variable, you will see that it is also a characterization of what we call Q, the classical Q polynomials. There are in total 12 plus 2 others that was found by Renato and co-authors. So for this, it was very strange for us that when we have this operator on lattices, we don't have the full characterization of Askew-Wilson polynomial, but just some specific cases. And when we were starting this, we thought that maybe this conjecture is not true, but even in substance, we will see that there is something wrong with this conjecture. So what we did is first to prove that if we have an orthogonal polynomial sequences satisfying that equation, then it is a classical orthogonal polynomials. So we show that there are two polynomials, phi and psi, of degree, I mean here it is psi, of degree exactly 1 for psi, and for phi it is a polynomial of degree and most 2, such that the Pearson equation holds. But at this point, the proof is not over because you can see that the polynomials phi and psi are in terms of some other parameters that are involved in the equations. That is why what we are going to do next is to show that the coefficients Bn and Cn of the polynomials Pn satisfying that equation fulfill a system of difference equations. And here we will see that are involved the parameter Cn, the coefficient that we have in the structural relation, and also the coefficients of the polynomials. That's why, in general, to solve this system, it is not easy, but some of them can be solved very easily. Like, for example, the first equation can be solved, the second one, and even the third one. But after that, this one is not so easy to solve. And even there is a fourth one where everything is mixed. So We will solve our problem taking into account three facts. First, initial conditions. This is because we know that classical orthogonal polynomials can be entirely determined by only the three first terms of the polynomials. And so, if we have initial condition where we have like B0, B1, C1, and C2, that information is enough to identify the polynomial because we already know that they are classical. So we know how the coefficients look like in general. What we are going to do is combine all this information, knowing that they are solution of this system, to give a positive answer to this problem. So we will answer positively this part, but I will later on come back to the second part of this conjecture. So now the situation of semi-classical orthogonal polynomials is the situation where we have a regular functional U satisfying the same Pearson type equations, but here we allowed the degree of the polynomial phi to be anything but no zero. And we allow also the degree of the polynomial psi not to be 1 necessarily, but greater than 1, greater or equals to 1. And now the second characterization is here, is the hand characterization, which is instead of the derivative sequence to be also an OPS here, it is quasi-orthogonal. That is the difference, and the definition here is given. And the third characterization is that this second order structural relation holds where in this site you can see a combination, a linear combination of terms, PNs, contrary to the classical one. And regarding semi-classical families, these families are difficult to describe. And that's why most of the time in the literature, they appear in a very strange way depending on the problem that we are solving. For example, in this problem, we will see that the semi-classical orthogonal polynomials are involved. What we were doing here is to consider the same structural relation that was posed in that other conjecture of Ismail, but the only change is that instead of multiplying a polynomial of degree, a fixed polynomial of degree 2 times the dx of pi n, in this side of the inequality of the equality, we put a polynomial of degree 1 and the operator sx. And this still makes sense because the operator sx conserves the degree of the polynomial, but the dx is a lowering operator, meaning that it reduces by 1 the degree of any polynomial. And so we ask again the same question: what are the orthogonal polynomial solutions? What we were able to prove here is that the polynomial involved solution of this equation fulfill the same system of difference equation that we had in the other case. But in this case, we saw that the polynomial solutions are not classical but semi-classical. And that's why sometimes these operators in the literature are called companion operator because they share some kind of similar properties. And here, since we don't know that, we don't know how to find the semi-classical families, we were able to describe some of them. For example, we proved that this classical, in fact, it is a specific case of a classical family, the continuous dual hand. We found that this polynomial is a solution of the system. More precisely, we proved that this equation holds. And later on, what we did is to manipulate that equation to arrive to this other equation that we have here in blue. And actually, this equation appears to be a counterexample to the second part of the conjecture, because Ismail said that the solutions of that equation remain unchanged if we allow the polynomial, the fixed polynomial pi to be of any degree, and if we add more term in the right-hand side of the equality. And so, clearly here we have a counterexample. And even more, in a very recent work with Kenya, we showed that This structural relation is related to the semi-classical orthogonal polynomials theory, and we were even able to find a new family belonging to the semi-classical one, and it is symmetric of class 2, and that family appears also to be a counterexample to other conjecture that was claimed to be proved in the literature by some other authors. And here I would like to share with you these last pictures that were taken during my thesis defense, and I still remember what we were talking about during these pictures. And in fact, after the thesis defense, when Kenya was taking this picture, Professor Petronino told me, but Buna, you got the maximum classification. Why are you not smiling? I said, but Prof, I have the mask. How can I smile under the mask? Who will see? Who will notice? He told me, okay, then you can remove your mask. And that's how we took this picture, because it was during the COVID period. Thank you very much.
Thank you, Duna, for your presentation and also for sharing with us these moments with Petronillo. Thank you very much. Are there any questions or comments to Duna? Even about something connected with PhD or other questions? Duna, I have a question. I'm not absolutely from your area,
Yes.
but when you said at a certain point that you have tried to unify the theory for many classes of the polynomials,
Yes.
for me it was not clear that you were able to arrive to this objective. Were you able to unify that theory for all classical polynomials?
I mean, the classical, what I present here is for the classical orthogonal polynomial on lattices. Yes, but even before that, the first one, as Renato presented during the first day of this meeting, this work was, he started with the standard derivative, and he was able to unify that, and later on, when I arrived, we extend that to the Hahn operator. Yes, and this now is the other work where we did it for the classical OPS on lattices.
Okay, thank you. Thank you.
Welcome.
So you have been clear, no one has questions to you. Let's thank Duna again. Next speaker is Edgar Labarga from the University of La Rioja. Is it right? So Edgar will talk. I have not here the title. I'm sorry for that. Very good. So the talk is about discrete appeal sequences in the Dunkel Z2 context. So please, Edgar, remember to be here above the light, close to the microphone.
In the 18th century, one of the foremost problems in the theory of the summation of series was to sum the inverse of the squares of the natural numbers. That is the Bassel's problem. The history was presented in the first talk of this morning by Professor Ribeiro, but let me put my work, my talk into context by reviewing some aspects of this problem. The first one who obtained a solution was Leonhard Euler in 1734, and he proved that the sum is equal to pi squared over 6. Later on, he also proved the following two identities. The first one can be viewed as a generalization of Bassel's problem, considering instead of squaring general even power. He showed that the sum is equal to some constants times the corresponding Bernoulli number. The second one of the identities is a kind of alternating sum and is related to what are called Euler numbers. Bernoulli and Euler numbers are particular evaluations of Bernoulli and Euler polynomials. Here we have the sequence. The first one is the sequence of the Bernoulli polynomials and the first terms of the sequence, and the second one is the Euler's sequence. They have many properties, but note that if we take one of these polynomials, for example b2, and take the derivative of b2, you obtain the degree 2 times the previous polynomial of the sequence. That's an interesting property that we are going to use in this talk. So let's go back to the identities of Euler, and if you rearrange in some way the constants, you can think of that sum in a way that you are summing the inverse of powers of the zeros of the sine function. And in the second case, you have the zeros of the cosine function. Well, there is a relation between Bessel functions and sine and cosine functions. So one can think in a natural way in the following problem. Try to sum the inverse of the square of even powers of the zeros of the Bessel functions. It's a kind of generalization of Euler's identity, and this was already done in this paper by Lord Rayleigh in 1873, but he didn't obtain a connection between this series and a kind of generalization of Bernoulli polynomials, or well, Bernoulli numbers. That was done in this paper from Oscar Ciaurri, Duran, Perez, and Barona, that was published in 2018. And the idea is try to generalize two frameworks. The first one is the framework of Appel sequences. What is an Appel sequence? An Appel sequence is a sequence of polynomials, Pn, of degree n, and they have the property that when you take the derivative of any of these polynomials, you obtain the degree times the previous polynomial. You can obtain a characterization of this definition in terms of the Taylor generating expansion of a function. That is, the polynomials appear as the coefficients of a Taylor expansion of some function, the generating function, which is of the form at, it only depends on t, times the exponential of xt. Why the exponential of xt? Well, because the exponential is invariant with respect to this operator, with respect to the derivative. So if you fix function at, you obtain a sequence of Appel polynomials. We already mentioned that Bernoulli and Euler polynomials have this property. So if you take this at, you obtain the Bernoulli polynomials, and if you take this at, you obtain Euler polynomials. So the idea is try to generalize this definition to try to sum the Rayleigh's function. And you have to consider a kind of Bessel context, which is known as Dunkel theory. Dunkel theory was introduced by Charles Dunkel in works in the late 80s and the beginning of the 90s, and it's related. It tries to generalize harmonic analysis in the framework of finite reflection groups. We are going to consider the most simple case, that is the group set 2. And here we have a kind of generalization of the classical derivative, that is the Dunkel operator. We have a parameter alpha that we are going to suppose bigger than -1, and the Dunkel operator is a differential operator. You have a differential part, which is the derivative, the classical derivative, and we have a difference part here. And you can see the action of the group here. Well, so if we denote calligraphical I as a kind of modification of the Bessel's function, we can obtain a function which is the Dunkel kernel, and this function is invariant under the Dunkel operator. The form of the Dunkel kernel is a generalization of the classical exponential, so you consider this series and you replace the classical factorial with a Dunkel factorial, if you want. Also, we have a kind of Euler's identity with the cosine and sine. So if you replace the parameter alpha and you make it equal to -1/2, you obtain that the Dunkel operator is the classical derivative and the Dunkel kernel, or Dunkel exponential, is the classical exponential. So you are generalizing the classical context. So we have all the ingredients to try to sum Rayleigh series and try to obtain some identities in the spirit of Euler's. Let me review the Dunkel set to context just briefly. We have an exponential, a Dunkel exponential. If you take alpha equal to -1/2, you obtain the classical exponential. You have a kind of Dunkel derivative, Dunkel operator. You take alpha equals to -1/2, you recover you have the classical derivative. You have a gamma, which is the generalization of n factorial. And then we can define Appel-Dunkel sequences in this context. That was done in the paper that I already mentioned and in some other papers before, after that. So the definition is the following. You replace you have a sequence of polynomials, which depends on the degree, half degree n, and there is a parameter alpha. Take the Dunkel derivative of any of one of these polynomials, and you obtain n, more or less n, because you have an alpha dependence, but n times the previous polynomial, Pn-1. The same definition as in the classical case, but with the Dunkel operator. And you can give a characterization of this definition in terms of the generating function, which now has the form AT times the exponential, the Dunkel exponential, the Dunkel kernel. So if you take this AT, you obtain a kind of generalization of the Bernoulli polynomials, and if you take this AT, you obtain a kind of generalization Dunkel polynomials. I mean generalization because if you take alpha equal to -1/2, you recover the classical case. So, well, so we have two contexts, but we are applying an operator, the classical derivative or the Dunkel operator, in a continuous way on the parameter x. What happens if you take a difference operator in a discrete case? You can define Appel sequences in this discrete case. So you define a discrete Appel sequence as a sequence of polynomial of degree n, and when you take the forward difference of these polynomials, you obtain the degree times the polynomial of degree n-1. You have also a characterization And now the function that appears, the generating function, has the form AT times the function that which is invariant with respect to this operator. It is a kind of exponential function, and when you take AT equals to this, you obtain the discrete analog of the Bernoulli polynomials, which are called Bernoulli polynomials of the second kind. And if you take this one, you should obtain the Euler's polynomials of the second kind, the discrete analog of Euler's polynomial, which are not called in this way in the literature, and the name is Boole polynomials, but they are the discrete analogs of Euler's polynomials. So our aim was try to generalize this discrete context to the Dunkel case, to the Dunkel context. So we almost did it in this paper of 2022, and in the following one also in 2024. So the natural idea is take an operator which is a generalization of the forward difference. Well, there is a Dunkel translation in the Dunkel context, which is a generalization of the classical translation. The definition is the following. The classical translation can be viewed in terms of the Taylor expansion where you have the derivative. So replace this derivative with the Dunkel operator. So you obtain the Dunkel translation. That it is a much more complicated operator, but and has this property. If you take the translation of the Dunkel exponential, you obtain the product of two exponential. Well, the idea is try to replace this forward difference with a kind of a generalization in the Dunkel context. So the most natural one, I think, is try to replace this term with the Dunkel translation by 1. Well, that problem, we are not able to solve that problem. If we consider this operator, we cannot obtain a function that is invariant under this operator. So we need to replace the forward difference by a central difference. Okay, we are not able to do this in this case, so we are going to take the central difference. If we define a central discrete Appel sequence in this way, you have a sequence of polynomials of degree n where you take the central difference instead of the forward difference, take the central difference and define the discrete central Appel sequences. In this way, you can characterize them in terms of a generating function of this form. This function is invariant under the central discrete difference. So the idea now is to replace this operator with this operator, a central difference in the Dunkel context. And now we can find the function that is invariant under this operator. What is that function? So we have to replace this by a function that is invariant under this operator. We thought that maybe if in this case the function is of the form an exponential of x times some function that depends only on t, maybe in the Dunkel case is the same. So we thought in that. Try to put here an exponential of x time, Dunkel exponential of x time a function that only depends on t, ht. You have to find ht. And if you make the computations, you obtain a function, this function g of h. So ht must be the inverse of this function gt. Then we can define the discrete Apel-Dunkel sequences in the following form. You define them considering the central Dunkel difference operator, but the important part is the characterization of this definition. The generating function has the form at times the exponential of x times a function that only depends on t, and that function is this one, the g inverse. If you take alpha equals to -1/2, you obtain the inverse of the hyperbolic sign. Well, so in this framework, we could define the analog in this discrete case of the Bernoulli polynomials, which are we called Bernoulli-Dunkel polynomials. You have to take this AT, and if you take this AT, you obtain the Boole-Dunkel polynomials, the analogs of the Euler of the Boole polynomials in the discrete case. Here's a brief overview of all what we have, which is the classical case. Bernoulli polynomials are Apel sequences because of these relations, and has this property. In the discrete case, the properties intertwine. So the Bernoulli polynomials of the second kind are Apel discrete because of this, and now they have this property. In the Dunkel case, you replace this derivative with the Dunkel derivative, and you obtain n times this, and they are Apel-Dunkel sequences. And our contribution was to define the Bernoulli polynomials of the second kind in the Dunkel context. They are Apel discrete because of this relation, and they satisfy some properties. Now here, this is a central falling factorial, but it doesn't matter. And in the Euler or Boole framework, instead of the forward difference operator that we had in here in the Bernoulli polynomials, in the property of Bernoulli polynomials, we have a kind of mean operator, but the relations are more or less the same. So I think that it is time to thank for the invitation to the organizers, and especially to Kenier. And well, congratulations for the conference to all of you, and thank you for your attention. That's all.
Thank you, Edgar, for the presentation, for the clear presentation. So it's time for questions or comments. Yes, please.
Thank you, Edgar. Very nice talk. I have a question concerning the evaluation of the reciprocal powers of the zeros of the Bessel function. Does that, in that evaluation, the analog of Euler's formula, does that appear your analog of the Bernoulli polynomials?
Sorry, can you repeat it?
You
mean the Rayleigh function? Yeah.
Yes.
Yeah.
If you take this, that series,
this one?
okay,
okay,
you get an analog of Euler's formula somehow.
Yeah, sure.
And
sure.
the Bernoulli numbers that appear in this formula, the analogs, are the same as that you got in the Dunkel context?
You mean we have here? They have, because I don't have. They have an analog of the Euler's identity.
Yeah,
okay, they have numbers of Bernoulli numbers. But they are not the same as the evaluation of in the discrete case. No, they are not the same. No. They are not the same. You have some polynomials in the continuous case, generalized polynomials in the continuous case, and we have another, other polynomials in the discrete case.
And
They are
can
not
you-
the same.
Okay, and can you relate with some kind of series analog of the zeta?
Yeah, I think so. I think we have some properties that relates the continuous and the discrete case.
Oh, that's nice.
Yeah, I think so. I can
But do you
send
have a
the
paper, or is still work in progress?
Excuse me?
Do we have a paper?
Yeah.
Okay.
I can send you the paper if you want.
Okay,
Yeah,
perfect. Okay, thank you.
Are there any other questions? Yes, wait a moment.
Thanks for your nice presentation, and I would like to know if, for example, you can extend this to the what we call the Q-Dunk operator.
Yeah, there are some works in this line of research. You can define the Apple-Dunkel sequences to that context of Q theory. Yeah,
Yes.
there are some works in that line. But in the discrete case, I haven't seen anything about that. In the continuous case, yeah, you can, there are some works. But in the discrete case, I haven't seen that.
Okay, thank you.
But that's a really interesting question.
Okay, thanks. Because I remember that I saw, when I saw that operator, I remember that there is also an operator called Q-Dunk operator.
Yeah, sure.
Yes, it's for the discrete case.
Dunkel operator is a special case of a certain Q operator. And it can be generalized to the Q-Dunkel Q theory. Yes, there is some literature in this line.
Okay,
Yeah.
yes, please, the last question is like, when you are talking about the Apple polynomials, yes, can you consider the orthogonality there?
You can, but we haven't thought about that.
Okay.
Yeah, but it is an interesting. This is an interesting question also. The orthogonality. Which polynomials are orthogonal in which Apple polynomials are orthogonal?
Yes.
That's
yes.
an old question in the classical case, but in the Dunkel case, I don't know anything about that.
Okay,
But-
thank you. Thank you.
Thank you. Are there any other questions? No? Very good. Let's thank both speakers again.
Thank you.
And now we have some minutes break because we will change from to Zoom sessions, presentations online, so the technical staff need to adapt the machinery. So if you want to be around here in 5 minutes, perhaps we restart, okay?
Hola. Hola.
Hello, Enrique.
Hi, how are you?
We would like to test the
Right.
sound.
Yeah, so what do you need to I say? Hello?
Hello. Now I will ask to the technical staff.
Right.
Did you hear? Is it
It
fine?
I'm hearing perfectly. Thank you. Hello. This is a drill to know if the sound is working correctly. Oof. Okay. Well.
Another test? No, it's not working, this one, perhaps, or other exit, okay. Okay, good morning. So good morning again. I don't know if it is working, this microphone. Yes. So we will start. Double voice. But okay, that's fine. We will start with the next speaker, Enrique Pardo, from the University of Cadiz. And the talk is about modeling groupoid algebras using left cancellative small categories. So I will close now.
Okay, thank you. Can you hear me? If so, I'll start by thank the organizers for giving me the opportunity of giving this talk in these conditions. I'm so sorry. And as you can see by the title, what I pretend to do is to, sorry, 1 minute. Okay. It's to show you a way of constructing groupoid sister algebras by using left cancellated small categories. First, the contents of this talk is a few part of the joint project that we carry with Eduardo Ortega that talked yesterday, and that can, at the moment, appears in these two papers that are published. If you're interested in them, you can ask either him or me for then some commercials. The first paragraph is about the people that paid for me participating in this research. And second paragraph is about the people that paid for Eduardo and I attending this meeting. In particular, thank you, Paquito and Fernando. And now let's go to the movie. The first I'll do is to outline more or less quickly what I'm trying to do. First, I try to motivate what's the interest of modeling groupoid sister algebras using categories. Then I'll quickly recall what's a groupoid, topological groupoid, and the algebras that are associated. I'll say the basic I need about left cancellative small categories in order to go to the main result in the talk, that is to explain how to construct the tag groupoid associated to left cancellative small category, and then to construct also the corresponding sister algebra. And hopefully, optimistically say, if I can say something about subset products, I'll do that. But just start a movie, and then I'll start with motivation. When we work in any topic, in particular in sister algebras, we're interested not only in proving theorems, that it's beautiful, but also in showing that the results has, say, control scope of their usage by having a large amount of families of examples that allows us to polite and refine the results. In the last 30 years, 40 to be precise, a concrete technique was developed in sister algebras in order to produce sister algebras, even in terms of generators and relations, associated to some combinatorial objects in such a way that you can use the properties of the combinatorial object in order to characterize the properties of the algebras. The first well-known example is that of Kurtz-Krieger algebras that were introduced in the early 80s by Joachim Kunz and Wilhelm Krieger, and that were, say, encoding the information of subshifts of finite types of symbolic dynamics to describe a very interesting family of sister algebras that gave rise to the study of purely infinite simple sister algebras, a very important class in theory. But since the object that they use are very restricted, also the class that you can represent was. And in the early 90s, Kunz, Paz, Reiber, and Renault extended the scope of Kunz and Krieger's construction and say defined sister algebras that they were associated to row finite countable graphs in such a way that algebras were given in terms of generators and relations encoded by the graph, and also the properties are encoded in terms of the properties of the graph. So you can characterize when the algebra is simple, that is a algebraic and topological condition, just looking at a couple of clearly easy to see in the graph properties. Moreover, because Jean Renaud was involved, they showed that these algebras also can be represented using topological groupoids, what now are called the Koenig-Renaud groupoids. And that's good because you can then study the properties of the algebra, not only looking at the, say, combinatorial presentation in terms of generators and relations, but also by using the well-known theory about algebra associated to groupoids. But also this family of algebras was too restrictive. When they started to compute the K-theory, the K0 and K1 groups, they realized that they cannot cover all the possible models of sister algebras, even for purely infinite simple ones. And then they started as a strategy of adding extra properties to the combinatorial object in order to extend the scope of the construction. And then you can find historically ultragraph algebras, lovely graph sister algebras that are associated to suffix shifts, high-rank graph sister algebra that generalizes the buildings of Robertson and Sticker, Katsura algebras associated to a couple of integer matrices, finite or infinite, with few properties, algebras that can be easily distributed and studied, also Nikozhevich algebras that are associated to self-similar actions of group form trees and their generalization to self-similar graphs where the action is given by groups and then by groupoids on finite and infinite graphs. In any case, all these families that extends the construction of graph sister algebras share some common characteristics. They can give properties of the algebra just looking at the combinatorial properties of the underlying object, and also they can be, say, represented as algebras of étale groupoids. The problem is that the zoo was going large and large, and then at the early 2000s, Jack Spielberg decided to boil up the common properties of all these models, and he concluded that the way of working all that stuff in a unique way is to use algebras associated to left-cancellative small categories. I will define that in a minute. And what he showed is that not only extends the previous classes and give the presentation in terms of generators and relations, but also he was able to show that there is a groupoid in such a way that the sister algebra of the groupoid coincides with the sister algebra that he defined for the left-cancellative small category. So the key point is that representing algebras using groupoids is an important tool. In another approach to the same situation, you can study the work of Alan Patterson in the middle 90s that he can generalize it the algebras associated to universal representation of groups, so to algebras associated to symmetries, to the context of inverse semigroups, so the partial symmetries of the spaces. And he showed that you can define for any inverse semigroup a universal sister algebra associated to the representations of this inverse semigroup. And moreover, he showed that he can, say, canonically associate a groupoid, that very well behaved groupoid, an ample groupoid, such that the sister algebra of this groupoid turns out to be the sister algebra universal for the representations of the inverse semigroup. The problem being that since the representations are semigroup representations, only keep track of the multiplicative relations, and then you cannot encode the additive relations that are needed to represent graph sister algebras or the other models. You only can represent the Toeplitz algebras. The way of solving this problem was found by Rui Exel that at 1998 showed that you can take a restriction of the Patterson's groupoid just by restricting the action of the inverse semigroup to a invariant closed subspace of the space of where you are acting to construct a Patterson groupoid. And then when you consider this new groupoid, the groupoid, then you can recover for the universal representations of this kind of groupoids, you can recover the CK2 type relations, the additive relations that were lost in Patterson representation, and then you can represent graph sister algebras, ultra-graph sister algebras, etc., using these groupoids. Moreover, the key point is that Rui Exel showed that any second countable ample groupoid is a large family. Are not all the groupoids that are used for defining sister algebras, but almost. Or any second countable ample groupoid can be represented up to isomorphism as a digroupoid of a suitable countable inverse subsemigroup of the groupoid. So there is a large class of groupoids that can be studied using an inverse semigroup approach. Then the natural question is, which is the connection between Excel, Job, and Spielberg's construction? There is any connection? And the answer is yes. And the first step was done by Dunsink-Millen, Lalonde, and other people that started by showing that when you have a left cancel of a small category, you can associate what they call a zigzag inverse semigroup. And moreover, that any inverse semigroup is Morita equivalent, almost isomorphic, to the zigzag semigroup for a suitable single aligned left cancel of a small category. So a left cancelled small category that is very well behaved, and what they did is to explicitly construct this left cancelled small category. So what they are saying is that you can represent any groupoid that is ample as the tag groupoid of the inverse semigroup of a left cancelled small category. But the point is that when this is finally aligned, the category is finally aligned, that was the first result of Edward and I, then the C-star algebra defined by Spielberg is the C-star algebra of the tag groupoid of this inverse semigroup. And this is essentially what I'll try to explain you in this talk. Certainly, that means that Spielberg algebras model algebras for second countable groupoids, and also means that because of the approach of Edouard and I, we can use a technology developed by Rui Excel and myself some years ago in order to determine the properties of the groupoids and then of the algebras looking at the combinatorial properties of the categories. In our project, we were centered mainly into things, subset product, that is a way of defining self-similar actions of groups or groupoids on categories. And also we were worried about the amenability of the associated groupoids in these constructions, because amenability guarantees that the C-star algebra, the reduced C-star algebra, and the full C-star algebra of the groupoid will coincide, and this is important for using tools that work in one of the sides or other of the sides. Now, let me recall quickly what's a groupoid and their algebras. A groupoid is a small category in which every homomorphism is an isomorphism, is a group with a lot of invariables, with a lot of units, but not any pair of elements can be, say, operated. And you can define, by using the inversion and the multiplication of the groupoid, you can define range and source maps from the groupoid to the set of units, that is the space of objects of your category. When the groupoid has a topology in which the operations and then the range and source map are continuous, we say that it is a topological groupoid. And when these range and source maps are local homomorphisms, then we have an étal groupoid. We'll concentrate in étal groupoids that are locally compact and the unit space is Hausdorff in the relative topology. Are the more common ones, and usually they are, equipped with a Hermitian, so it's very good. And when we stress the conditions on the unit space of an étal groupoid, and we ask the groupoid to be the unit space to be zero-dimensional, so say topologic, totally disconnected, then we have what we call an ample groupoid, and this is the kind of groupoids we will work with. Once you have an étal groupoid, you can consider the linear pair of set of continuous complex valid compactly supported functions on G, then define a convolution product. Here, the only problem is to prove that this, say, sum is finite, but this is true because some compactness conditions that applies, and also you can add an involution on this set of functions, so you can endorse this set with the structure of complex star algebra, and then taking suitable norms, you can construct the full and the reduced C-star algebra associated to a groupoid. I will skip all the nasty details, and I'll skip to the left cancel of small categories, and then in this case, what we have is that a small category is essentially a category with the objects and the morphisms are sets. You can consider for a model in your mind, you have a directed graph, then the vertices are the objects and the finite paths are the maps. And then with this idea in mind, you say that the source of a map is its domain and its range is the range of the map. and we fix the right invariable elements as the maps that has a right inverse. Left consolidative means in this context that whenever you have alpha beta equal alpha gamma, then you can, in fact, say erase alpha. And categorically, that means that all the morphisms, in this category are monomorphisms, and in particular that right, left, and to say that the invariables coincide. If you want to skip inverses, then you must restrict to the situation where the only inverses in your category are the units or the objects. Then, in order to do some theory, meaning what's done for graphs, rank graphs, etc., you need to consider the notion of extension of a map, and essentially beta extends alpha. If beta is factor out through alpha, being alpha the first map the last map that you're using, and we denote by this in this way the set of initial segments of the factorizations of any map that endows your category with a partial order. We also need the condition of common extensions that makes sense if you think in maps. So you're mapping from one set to another, and then if you're going through these source and range sets through factorizations, but if these factorizations of the map coincide with the original one, then the original maps that you're putting in first site are exactly the ones that has as common extension the map from the source to the target. It's something like that. And then under mild conditions, you can ask the existence of, say, minimal common extensions. And using this idea of minimal common extension, you fix the property of being finally aligned that is satisfied by mostly of the examples I put it. And category is finally aligned if whenever you have two maps, then there's a finite subset that the common extensions are generated by extensions of this finite family of maps. When the set of maps that are common extensions is singleton, then we say that is singly aligned. And finally, in order to express the algebras of Spielberg, I need to talk about what is an exhaustive set. So I fix the notation alpha intersection beta when they have a non-empty common extension. And we say that a subset of a set is exhaustive in the big set if whenever we have an element, a map in E, then it has a common extension with at least one element in the subset S set. And we will need to fix all the finite exhaustive subsets of any element in your category. And now let me talk about this tag groupoid. So the algebra defined by Spielberg is the algebra universal algebra given in terms of generators and relations, where the generators are associated to the category, and the relation says the first one that all the elements, all the generators are partial isometries, and if alpha is a object, then are projections, that it keep track, second relation, of the composition of morphisms in the category. The third says that range projections set to morphisms in your category decomposes as a supremum of the projections set to the minimal common extensions of alpha and beta. And this is what is called CK1. And CK2 says that the projections set to any object factor out as the supremum of the range projections associated to any family of finite exhaustive sets starting in B. This is the presentation, and this while up the presentation of all the algebras in the large, say, list of families I've presented. And what he did was associated an ample groupoid to this presentation, and he showed that the full sister algebra of this groupoid corresponds to the above algebra. And what we do is to take advantage of the picture of Riexel that you can represent any groupoid, in particular Spielberg's one, as a groupoid of a tag groupoid of an inverse semigroup. And then, but we will show is that this inverse semigroup that appears in the case of Spielberg's model is exactly the six-up semigroup of Donsick and other people. So let me first present who is this inverse semigroup. you pick any left cancel of a small category, and then you define partial bijections into the category that goes from alpha lambda to source of alpha lambda is a destruction operator, and from S of alpha to S to f of alpha lambda to alpha lambda, that is a construction mapping. And then since these are partial bijections into lambda, and the set of partial bijections is our set is always an inverse semigroup, you can produce the inverse semigroup generated by these two operators. In the case of finally aligned left cancel of a small category, the elements in this semigroup has a very helpful presentation, but I'll skip that. And now what I need is to construct the groupoid. And for constructing the groupoid, I need to construct data importance on this inverse semigroup, then the filters, then completing the topology, the ultra filters to get the tag filters, define a action by partial homeomorphisms, and then construct a groupoid. But this is quite involved, and what Eduardo and I did was work directly with the category, skipping idempotence and skipping also filters, etc., and replace that by a space of hereditary upwards directed subsets of your category. Hereditary means that inherits to be in the set if they are dominated above, and that and any pair is dominated above by someone. And then we equip this set with the topology that turns out this set a locally compact Hausdorff total disconnected space. And then we define which are the maximals. And since we have a topology, we complete the maximals, and we talk about the, say, tight hereditary upward directed sets. The point being that the set of hereditary and upward directed sets is homeomorphic in this topology to the subspace of prime filters of the left cancel of the inverse semigroup of lambda. And then you can extend that in such a way that you can show that the maximals sets are homeomorphic to the ultrafilters, and then the tight hereditary sets are homeomorphic to the tight filters. So we are encoding in a more say friendly way the construction of Riexel, and then in this case it can be easily construct a model of the action of the elements of the inverse semigroup on the elements of this set lambda star. The formula is like that. And because this induces partial homomorphisms defined by the action of this S from the domain to the range of the action. And the action is continuous and extends not only to the ultrafilters, but also to the tech filters. So it's the same in our language. And then we can define what is called the transformation groupoid of this action, that is a set of pairs as F, where F is a set that is in the domain of the action of S. The range and the source are clear how are defined. The product is defined when it makes sense, when they connect, and you can define the inverse. So you get a groupoid that is a ample groupoid. And then in order to avoid redundancies, you factor out through the germ relation. That means germ relation essentially is to say that SF coincides with TG if G, F, and G coincides as sets, and then S and G, so S and T as partial homeomorphisms coincide on a neighborhood, open neighborhood of the element F. Then you factor out, you get this groupoid that is, by the construction that we did, is the tight groupoid of the inverse semigroup in Excel terms. And then what we did, and was the most difficult part of our result, was to show that this groupoid is topologically isomorphic to groupoid defined by Spielberg. That was a very, very involved construction, that of Spielberg, so you cannot compute effectively the groupoid or say anything. And then using that and results of Riexel and myself, then we were able to say, characterizing combinatorial properties, in terms of combinatorial properties of the category, we were able to characterize properties of the groupoid, and then, for example, to characterize when the C-star algebra of the groupoid, the groupoid associated to this category, is a simple algebra. We did more things, but that was okay. And I think that my time's over. So I'll only signal that there are two typical examples of application. One is change the construction of Rabun and all that people about graph sister algebras. And then if we change the graph construction by the category of finite paths, then we obtain a better picture of graph sister algebra in terms of groupoid sister algebras. And same happens when we study the construction of higher rank sister algebras by considering the category of finite words on finite paths on the category. And I think that's all I want to say because my time is gone. So thank you for your attention. And if you have any question, I'll say open. Okay. Hello. Are you listening
Thank
me?
you, Enrique, for your talk. Are there any questions or comments? No, I have a small question. Perhaps it's a rather appropriate question. I do not know. But you, at a certain point,
Could you repeat your question, please?
I don't know if this one works. Are you able to listen me, Enrique? No. Are you able to listen?
Yeah. I listen to you.
Okay. I have a question. It's perhaps not appropriate question, but at a certain point, you talked about graphs.
Yes.
And the graphs have many applications on networks and many other structures. Do you know if in particular this abstract theory is important at the level of some particular applications?
As far as I know, the answer is no. We are all interested in the graphs just in terms of say picture, the generators and the relations of the algebra we were working with, but we are not really interested in the properties that are interesting for people that works in graph theory. In particular, we're working all the time with directed graphs, not undirected ones. That means that for applications to networks, to electrical sources, to all that stuff, the results we work with doesn't apply at all. I'm sorry.
No, thank you very much. Thank you very much. So we thank you again. Emmanuel, good morning, good afternoon. Can you say something to us?
Yes, I can say, but I don't see the possibility to share my presentation. I don't know why.
Perhaps exit and enter again.
Okay, I do it now. Thank you. Okay. No, same problems. Can do it. If I do it, that's strange. So now my screen. I don't hear you.
Are you familiar with Zoom?
For sure. Yeah, I'm familiar with Zoom.
Okay, just to understand the level of the difficulty.
No, the level of the difficulty that when I go to share, he give me, I don't see the PDF. That's it.
But are you sharing the entire screen, or perhaps you are sharing another particular part of the screen?
Sure. Now I share the entire screen.
Okay. Yes.
Okay, here we are.
Here we are. So it is my pleasure to introduce Emmanuel Guarilla from the University of Venzu Kin. I'm not sure if it is a correct pronunciation. So Emmanuel, after this starting not so amazing, you have the floor. Please, you can start. You have more or less 25 minutes. Please.
Okay. Okay. So thank you. Thanks for the nice introduction. So in this talk, we will see some remarks of fractional calculus, the case of zeta function, and at the end we will see my recent my new research interest in Sobolev space, Sardi space. It seems that this fractional derivative works well with function with function space, which is a surprise for me as well. So let's see something. Let's start and let's see some remark that all of you know what. Almost all of you should know what is the Riemann zeta function, but for reason of completeness, we see the definition here. And in the same slide, I show to you the definition of fractional derivative. This is the Grunman-Letnikov derivative. This is the fractional derivative that best fit with this complex function. Now, in this talk, I will not discuss about the problems that currently have with the definition of fractional derivative. However, my results, I obtained the same results using almost all the fractional derivative that currently have. Why this is the best definition of fractional derivative for this problem? because this definition satisfies a generalization of the Leibniz rule, and this helps us a lot, especially in terms of functional equation. So using this definition is very easy. Here we have a binomial series. We can get the alpha order fractional derivative of the Riemann zeta function. Okay. So one problem when we use go to use the generalization of the Leibniz rule is that the generalization of Leibniz rule give us a functional equation, and we have a triple summation. This problem can be avoided using an apostole already proposed by Apostol and Spira for the integer derivative of the Riemann zeta function. That is, we work a little bit with the complex exponential. This is what Apostol and Spira did in 60 and 70 years. In the same way, we can prove that there is also an equivalent of the symmetric, because the Riemann zeta function has a symmetric functional equation, and the same holds for the fractional derivative. So T of alpha is, let's say, is almost equal to T of alpha 1 minus S, where this is T alpha of S. But here we have a double summation, and this symbol means that this is true up to a multiplicative constant. This multiplicative constant is an exponential that involves alpha. Okay, so I also proved these results in 20 and 21. These same results can be generalized to generalization of the Riemann zeta function, i.e. Dirichlet series, Harvey series, Lerch zeta function, and so on. Here now, so the point is how we can work with this fractional derivative and use this for a class of zeta function. Well, we can treat the case of the Lerch zeta function. Lerch zeta function somehow generalize several zeta function. So again, this is the generalization. This is a function that for if you know you had a class of special function, and using the same technique, i.e. the Grunwald technical derivative, even if the first time I use the Caputo derivative. If you use the Caputo derivative, you have to close an integral that generally is an Euler gamma. If you use this Grunwald technical derivative, you use with binomial series, so you get this result. And well, this is just a sketch of the proof. We don't stay here because we have just 25 minutes. So the Grunwald technical derivative of L is this limit. We can interchange here sum and limit. We don't have problem. We have a uniform convergence. And at the end, in the last right-hand side, we have a binomial series. Okay, so we can reach it this way. Here, if you want to get a functional equation, we also have problem of computational cost. We can again work as in the case as proposed by Apostol and Spira. We have here just one summation, and these results come directly from the Rademacher formula of the Lerch zeta function. Well, basically, we have this. This is what. This is how this is the Apostol technique. Okay, so the Apostol technique first you have to manipulate a little bit L, and the second we must introduce an auxiliary function psi of L. In the case of the Riemann zeta function, we have a psi of zeta. Okay, so it's easy. At the end, we have that L is written as the sum of these two functions with different parameters, and so the fractional derivative of L will be the fractional derivative of these two conjugates. There is a way to link this fractional derivative with prime numbers. The first theorem here is the classical expansion of the Dirichlet series in terms of Euler product. For Fn equal to 1, we have the case of the Riemann zeta function, and this is the classical infinite sum that generally mathematicians know about the Riemann zeta function. But the problem is that this is true when f is completely multiplicative. What's happened when this is not completely multiplicative? Well, this is a problem that actually I solved. And the point is that here we can write this product, this sum as a product, but the sum inside doesn't converge. Moreover, we can compute the fraction log derivative of zeta. And regarding the critical strip, if we introduce the Dirichlet function, we remember that the Dirichlet function converges when r of s is greater than 0. So, since the Riemann zeta function converges for r of s greater than 1, the critical strip is fixed by the convergence domain of these two functions. Likewise, the fractional derivative of eta converge when r of s is greater than alpha. So it seems that their fractional derivative give us a strip alpha 1 plus alpha. Okay, so basically we have this. So this fractional critical strip shift, there is a shift according to alpha. In the same way, we can fix zero region. This technique depends. No, this is a technique like head and tail, and was proposed for the first time in 2020. Okay, so here how we get the so we see this for the Harvey zeta function. So how does it work? First, we take the n term of the series 3, and so the point is to find the dominant term. Okay, so the term for which here q of capital N is greater than the rest. Okay, so basically what we want to solve, we want to solve that q of n is equal to q of n plus 1. For sure, these terms depend on a because the Harvey zeta function depend on a. So in the case of Riemann zeta function, this we will have that this term here is q alpha n 1. So the solution is this q, and that's quite easy. That's quite easy. Okay. So now what we will have? We will have that the Harvey zeta function has no zero in this wedge q n a alpha plus b1. And I mean the right hand side is q n minus 1 a alpha plus b2. So how we fix b1 and b2? b1 and b2 are fixed when we find the dominant term. And the dominant term is, we get the dominant term using this equation that we saw before. Okay, so now we arrive to the main point. So we split our term in head, h, and tail. Okay, so that's quite easy. So we split this. Why we split it this way? Because the term n equal to n, small n equal to capital N is our dominant term. Okay, so our main aim is to find this. Okay, so if we find this, okay, we get that zeta alpha as a doesn't vanish. Okay, so I found this zero free region in 2023. Currently, I will work now in another direction that I explain you now. So we have for sigma greater than q2a alpha plus 3.2, we have that the Harvey zeta function is not zero. So this is a zero free region, and for sure this works for all a such that the Harvey zeta function exists. Okay, okay. So after I will show you the references. So this has some corollary. For instance, for every d greater than 0, there exists a gamma real such that if sigma is greater than gamma, so we have a zero free region. And this other theorem where we find some domain where zeta alpha SA, so our Arvin zeta function has just 1 0. So this is not for a zero free region. So, for instance, that's a plot. So here, the wedge we see here in green, in yellow, and in dark blue are our zero free region, and this correspond to the second theorem here, and better than better to this definition here for sigma. Okay. Now my research will move on function space. Why? Because if we come back here, we see that this fractional derivative, why it's so special? Because it's equal to the integer derivative of Riemann zeta function. Just we have to replace alpha with n, where n is the integer order of differentiation. So this means that probably we can, for instance, we could define a function space that has this property. Moreover, we can study this function in the fractional Sobolev space WSP. These nowadays in fractional calculus, these are are well-known spaces. The same for the hard space and fractional Laplace operation, for the regularity, and so on. Okay, so these are my references. You find the main results you saw in the first and second paper. If you want the definition of Gromov electrical derivative to the complex plane, see this paper of Trujillo, or maybe better, the last paper of Lee, Dow, and Guo for fractional derivative in complex space. And you find some results of the fractional derivative of the Arvin zeta function. The first paper, while the link with primes is discussed in this paper published in Advancing Distance Equation. Last two papers show the techniques used by Apostol and Spira, especially this paper of 85. If you go in this paper, you find also a lot of details about the zero free region. Thank you.
Thank you, Emmanuel, for the presentation. Any question?
So, any question? Okay, any question?
Thank you for the nice talk. I have a question concerning a paper by Bruce Berndt, 2 years after Spira's result. He proved that that the number of zeros of the kth derivative of the Riemann zeta function was related to up to height t in a rectangle, complex rectangle with height t, is related to the number of zeros of the Riemann zeta function plus a factor which depends on t. Do you have a similar result for fractional derivative?
No, because the fractional derivative of this function, as far as I know, was discussed a long time ago, little bit, and after I wrote my PhD thesis on this topic, and there was also another scholar that wrote his dissertation after me, Ferran Hernandez. And so now people seems that there are some new interest, but in 60, 70 years, nobody dealt with this topic. So we have some topics, we have some results which are very, very similar, like could be the critical strip, the functional equation, and maybe now we can, I am confident that I can do something that I can do something with function space. But there are other topics which are totally different, and this depends on the difficulties that we currently have in fractional calculus. And we have a lot of difficulties in fractional calculus. Thank you for your question.
And another question. There are some some error terms for the number of zeros of the kth derivative of the Riemann zeta function, which depend on the Riemann hypothesis, like some very strong whole terms like log t over log t. Do you have analogous also for? Do we have some conditional results on the Riemann hypothesis in your results?
The point is that we should formulate. My opinion is that we should formulate a sort of fractional Riemann hypothesis, and we should prove that under some conditions the fractional Riemann hypothesis converges to the classic Riemann hypothesis. So if we do this, your question makes sense, and these results are of great interest. If we don't formulate, if I don't, or if scholars will not formulate a fractional Riemann hypothesis, we cannot do this.
Okay.
But this new strip that is function of alpha maybe will allow us to formulate a fractional Riemann hypothesis.
Okay. Nice.
Thank you.
Thank you.
Thank you.
Excuse me, one more question. Perhaps you have some, do you have some criterion of equivalence for the Riemann hypothesis involving fractional derivatives?
No, as far as I know, there are not this criteria. I want to, so you mean for a general definition of fractional derivative or for this fractional derivative?
This kind or any another type of fractional derivative involving zeta?
No, as far as I know, there are no criteria that involve, because as I told before, my hope is that we find a fractional Riemann hypothesis. Okay. And we should prove that under some conditions, the fractional Riemann hypothesis converges to the Riemann hypothesis we know. And this would be a very nice result. So thank you for your question.
But kind of if and only if you don't have, no?
No, we don't have.
Okay, thank you.
You're welcome.
Are there any other comments or questions? No, thank you, Emmanuel. We thank also all speakers of this session, of both sessions of this morning. So thank you also here, all the participants in our room. Let's close the session, I think. Organizers, can we close the session? Yes, we can. Thank you.
Thank you. Bye, bye, bye.